This kind of work is that I've done in collaboration with Orr and Rapkap in a variety of papers over the last few years. I haven't worked on this in the last year or so, so I might be a little bit rusty, but let's see what I can do. Although recently I started looking with Rapkap at some generalizations that I will perhaps allude to later in the talk. So this is a talk about algebraic structures which emerge in M theory. And if you're interested in M theory, that's good. If you're not interested in M theory, I hope you will still find the structures interesting. I believe that the perspective offered by M theory gives some nice way to think about a variety of properties of W algebras and the doubly deformed current algebras and fine Youngians and whatnot.
So most of the statements can be still rephrased as perturbative string theory, just maybe not as elegant.
Right. So when you try to express it in string theory, you lose symmetries. So I think M theory is the natural setting to discuss them.
Of course. Yeah.
But I will discuss that briefly. So because of that, I will give a brief introduction of about the facts about M theory that I will need for the rest of the talk, which are not many, but as we were mentioning. So M theory is conjecturally a UV completion of 11-dimensional supergravity, and it's expected to be rather unique, to have no continuous parameters except for the scale which sets the Planck, essentially the Planck scale. The fact that it's a UV completion of supergravity means that at low energy, you have the supergravity action. And on top of that, there is an infinite tower of irrelevant deformations which correct this low energy behavior. And this infinite tower of irrelevant deformations is not something we at the moment know. So we can compute some of them with a variety of means using dualities or relationship to string theory. This low energy effective action presumably is strongly constrained by supersymmetry. And there have been quite some notable recent progress in employing ideas from holography and from the S-matrix bootstrap to gain information about the effective action of M theory. Now this kind of problems is very far from algebraic. It's typically very analytic, but I'm going to discuss a sort of simplified setup where these sort of ideas can be manifested in an algebraic setting. And so I will not discuss further the ideas of holography or bootstrap, but they are in the back of they're sort of the background for what I'm going to talk about, and they definitely influenced this kind of work. And my hope is that vice versa, these sort of algebraic constraints can be then fed back into into our understanding of the physical theory, and might provide as input for a bootstrap. The main feature of M theory that I will use is that it is supposed to admit some dynamical objects, which are called shoe-brains and M5-brains. The sort of three-dimensional and six-dimensional membranes which move in this 11-dimensional space-time and locally preserve half of the supersymmetry. At low energy, you should think about these membranes as really some objects which support some quantum field theories, which describe the deformations of these membranes, and which are coupled to the supergravity theory. And again, there is sort of a leading three-level coupling, classical coupling, and then there are presumably a whole infinite tower of irrelevant couplings, which at the moment we just don't understand or don't know about. And a general idea that is in the back of my head and has been, I think, partly manifested by some work by Costello is that the variability of being able to couple this bulk theory to these defects should strongly constrain the properties of the bulk theory. So kind of my hope is that at some point we'll be able to use just the fact that these D-branes exist in order to constrain all of these couplings both in the bulk and on the branes. But at the moment we are very far from being able to do something like that. How do these theories that live on the membranes look like? If you have a single M2 brane or a single M5 branes, the theories are just the supersymmetrization of what you would expect to see on a membrane. So there are some degrees of freedom which describe the motion of the membrane, infinitesimal fluctuations of the membrane. And then there are supersymmetric patterns of them. But if you start bringing together multiple M2 branes or multiple M5 branes, then you find much more intricate and rich quantum field theories. Some strongly coupled superconformal field theories, which are of rather, they're interesting for a variety of purposes. Another piece of information that I need from the physical theory is that these membranes admit a variety of junctions. So these membranes can intersect in various ways, M2 branes can end on M5 branes, and this junction preserves some supersymmetry. And again, at these junctions, there will be some extra degrees of freedom, there will be some extra couplings to both the theories and the branes and on the gravity theory. And the whole structure should be constrained by all sorts of consistency conditions, which you don't really understand at this moment. What I want to discuss is, as I said, this twisted M theory setup, which was introduced by Costello, and which you can think about it as essentially a protected subsector of M theory. Intuitively, you're sort of taking the cohomology of M theory with respect to the action of one of the supercharges. So the effect of this operation is to reduce this eleven-dimensional theory of gravity to a much simpler theory, essentially in 5 dimensions. So what's going is that one turns on a certain thing called omega deformation, which sort of prevents everything from moving in 3 of the planes of this 11-dimensional space-time. This omega deformation comes with a parameter, and so here we have 3 parameters, one for each plane, and the 3 parameters add up to 0. Essentially, it's a sort of a Calabi-Yau condition. And so after this twisting, you get a 5-dimensional theory. It's a theory which is topological along R and holomorphic symplectic on C2. It's a kind of a bizarre piece of the theory of gravity. And roughly the gauge symmetries of this theory are complex symplectomorphisms of C2. Now, I want to stress that while in the previous slides we were in physics, and you could take these statements as sort of emotional from the point of view of a mathematician, here we are already in mathematics, in the sense that there is a well-defined notion of a factorization algebra of operators, of local operators of a theory in R times C2, factorization algebra which is topological holomorphic. And so you can state mathematically the problem of determining this factorization algebra. And this factorization algebra will capture some of the properties of the bulk of the low energy effective action of M theory. And part of what I would like to understand very much is which part does it capture, but that's not for today. Before I continue, I would like to also stress that this is one particular twisted M theory background. There is a variety of them. There's this sort of internal 6 directions can be replaced by essentially any toric Calabi-Yau. And this can give you various generalizations of what I'm going to discuss today. So while today I discuss things related to a sort of a, GL1 affine Youngian, there are generalizations to GLK/K prime, or D2 alpha, which can be accessed by looking at other toric Calabi-Yaus. Okay, any questions at this stage? Okay. So, what happens? So it's rather tricky to talk about these 5-dimensional factorization algebras. although they are defining, in principle, they are well defined and understandable, extracting what are their properties and their data is still somewhat of a challenge. A useful idea is to look at what happens to the various defects of M theory, to the dynamical objects of M theory after twisting. Because these objects have sort of a lower dimensionality, and so you encounter factorization algebras which are easier to understand. So in particular, if you look at M2 brains are originally three-dimensional, but they, in twisted M theory, they end up wrapping one of the three internal planes. And so instead of one three-dimensional object, after twisting, you get three types of particles, three types of one-dimensional objects, which move in R times C times C, essentially wrapping R and fluctuating in the holomorphic directions. The volume theory of an M2 brain is now one-dimensional topological theory, which means it's essentially captured by an algebra, the algebra of local operators. And as we have three types of M2 brains, and we can stack them, there are junctions that allow you to put transverse M2 brains. You can take three stacks of M2 brains wrapping the three planes, and 1 and 2 and 3 of them. And the result will be some algebra labeled by these three integers and by the three deformation parameters. And one of the objectives of my work with Miroslav Rapka was to figure out what are these algebras. Because, so if you have a single M2 brains, the algebra is just a Weil algebra. Pretty much, there are two generators which describe motion in these two transverse complex directions. And for some reason, these M2 brains feel a bit of a non-commutativity, which depends on which plane they wrap. And so this algebra is a Weil algebra. And Kevin used the duality to show that the algebra associated to a stack of n M2 brains wrapping the same plane is the quantization of the algebra functions on the Hilbert scheme of points in C2. But so what we wanted to sort of complete the story to figure out what is the most general algebra. And the strategy we have in mind is that there should be a way to combine parallel M2 brains into a stack. So there should be a way to reconstruct, to fuse line defects and to constrain line defect, the algebra on a complicated line defect, on a complicated stack of brains, in terms of the algebras on the individual brains. And also, right, we would like to understand, I will also, we'd like to understand better what does it mean to couple these M2 brains to the bulk theory. So in the physical theory, these M2 brains are coupled to supergravity. Here in this twisted theory, this M2 brain algebra is coupled to this 5-dimensional factorization algebra. And we'd like to understand a bit better what does it mean and how does it constrain the factorization algebra. Similar considerations can be applied to M5 brains. M5 brains will wrap in a holomorphic plane in the 5-dimensional space-time, and two planes in the internal Calabi-Yau. And so on this, so you get three types of strings, three types of two-dimensional holomorphic objects instead of one-dimensional topological ones. And the local operators on an holomorphic object form a chiral algebra. And so to each of these types of M5 brains, you can associate some vertex algebras. And if you have three stacks of M5 brains, you get some complicated vertex algebra, which depends on the choice of these three numbers of three integers of M5 brains on each stack. If you have a single M5 brain, the vertex algebra is just a current algebra, U1 current algebra, Heisenberg algebra, which roughly describes the position in the second C, the one that's not wrapped by the brain. Using a type 2B construction with Miroslav in previous work, we had proposed some vertex algebras which represent the most general case of three intersecting stacks. We built them as Drinfeld-Sokolov reductions of certain Kac-Moody algebras or superalgebras. A very special case when you have a single stack of M5 brains is the standard W algebras, Wn algebra, with a level which is the ratio of two epsilons. And again, we would like to understand better how are these algebras coupled to the bulk theory, and in which sense we can fuse defects to produce more complicated stacks. Any questions? Okay. Finally, we would like to understand better the role of junctions in this setup. I can have M2 branes wrapped in the real direction, which intersect M5 branes wrapped in the complex plane. I can, because M2 branes can end on M5 branes, I can have different numbers of M2 branes on above and below the intersection. And whatever local operators live at the intersection will be a module for the local operators that live on the defects, on these dynamical objects. So you get a module for the product of these two algebras and a chiral algebra.
So Davide, in these examples with M2 branes and M5 branes, so algebra is staggered by correspondence, right? So, what can you remind how what happens on the brane level? So, like when algebra acts on the Hilbert space, generator acts on the Hilbert space, how is it realized? Or just
these are all relative theories, so there is no really, you don't really have a Hilbert space. There is no space of states, but you can have these modules of local operators which live at endpoints or at junctions.
Okay, so like more like deformation, quantization, construction, which gives you just the algebra, right?
Yes, that's right. Now, for example, if you have a situation where M2 branes just end on M5 brane, we argued in the paper with O that the local operators at the endpoint should form a highest weight module for the algebra on the M2 brane.
Mm-hmm.
And for the work with Miroslav, we also had reason to believe that this local operator should also be a degenerate module for the W algebra on the M5 brane. And what I want to understand in this most recent work with Miroslav was, so we know we have some coupling of the bulk theory to both the M2 branes and M5 branes. Essentially, this is like a gauging of some sort. And now, after you couple to this gravity or gauge theory, the only junctions that survive will be the ones that are gauge invariant. And so the expectation is you should be able to find a gauge invariant junction for every physical system we know should exist. So this gives some intricate relations between the properties of modules for these algebras and chiral algebras. And following these relations along, we stumbled on what I find very nice physical explanations for phenomena like the appearance of Calogero models when you study the degenerate fields of W algebras, or the Mura construction, or the Coulomb gas construction. A lot of very basic facts about W algebras or about these Calogero models seem to have a justification or an explanation in the context of this twisted M theory. And just by blindly, not blindly, but just by following this sort of ideas, we could already find some new results, like new representations of the new Calogero models or other things like that. And as I said, this is just one example of a class of generalizations that can be realized by changing the internal manifold.
Okay.
So, okay, any questions? So let me first describe what does it mean to couple these defects to the bulk theory in mathematical language. So Kevin used the idea of Koszul duality to encode the couplings to the bulk theory as algebra morphisms. So for the M2 branes, he proposed that these couplings are encoded as a morphism, as an algebra morphism from the deformed double current algebra that I note here as A, epsilon 1, epsilon 2, epsilon 3, to these volume algebras of the M2 branes. And similarly, for the M5 branes, he conjectured that there should be a chiral algebra, which is essentially W infinity, and which should have a morphism into these Wn1, M2, and 3 chiral algebras. And a way to understand these A or W algebras is that they are versions of the gauge algebra of the bulk. So if you were in a sort of a three-level situation, ignoring quantum corrections, the gauge algebra in the bulk would be just symplectomorphisms of C2. And the form W current algebra or the W infinity algebra are both nonlinear deformations of this sort of the algebra symplectomorphisms on C2.
So are those arrows truncations in a sense?
Well, they happen to be truncations. That's right. So there is an idea in both cases that you can quotient by, I think. But the causality statement, I think, is just that there is a morphism.
Yeah, so like a surjective map from left to
yeah,
right.
I'm not sure. So right, it's not clear to me that it should be surjective, to be frank.
So the example that I know is quantum toroidal to Daha, right? To gel and Daha. It's one of those, right? So basically, you need to
yes. Right. If you like your algebras more elliptic or toroidal, you should sort of take the setup I'm discussing, replacing C2 with C times C star or C star times C star.
Yeah. Then
you will get, gel hat 1 or things like that.
Okay.
So here, very concretely, these morphisms essentially mean that inside these algebras, these algebras sort of give a representation of the generators T and M of the form double current algebra, or the currents Wn of the W infinity algebra. Okay. How do these morphisms look like, and what are these examples of this algebra? So, as I mentioned, if you take just a single stack of M2 branes, you get a quantization of the Hilbert scheme of points in C2. And the double deformed current algebra is sort of a uniform in N version of that Hilbert scheme. So if you write the Hilbert scheme as a upper-Kähler quotient based on the ADHM quiver or some UN gauge group, then you sort of take N to be you ignore trace relations and you get this doubly deformed current algebra. But a realization that of the doubly deformed current algebra, which is more useful for today's discussion, is that of involving the Calogero model. So this algebra is essentially generated by the Calogero Hamiltonian together with the symmetric polynomials in the positions. So if you define T0D as the symmetric polynomials and T20 as the quadratic Calogero Hamiltonian, then taking commutators of these, you generate all these T and M generators. Now, you can use this representation of AN to find a meromorphic coproduct for the W deformed current algebra, which essentially maps A to A tensor A in formal power series in Z inverse. Basically, what you can do is you can take a subset of the Z's, shift them by some Z, and expand an inverse power series of Z. And then these T's are rewritten as sort of polynomials in two individual sets of T's that involve part of the variables. So essentially, the way we produced A and 1 and 2 and 3 was by using this meromorphic product. So the algebra, you see this Calogero representation, the algebra clearly treats epsilon 1, epsilon 2, and epsilon 3 in different ways. But the algebra itself is symmetric in epsilon 1, epsilon 2, and epsilon 3, the permutation of these three epsilons. So you can use, and this coproduct is also symmetric in the epsilons, although it's far from obvious. And so you can use this coproduct to sort of glue together Calogero Hamiltonians oriented in three different ways, and then resum to get something like this. So this gives you sort of a Calogero representation of the most general algebra that comes from M2 branes. It's some kind of a, so in a talk earlier, I think on Tuesday, I think there was which was mentioned in an isotropic version of the Calogero model, where there were two different types of positions. This is slightly more general. Hamiltonian, we have three different types of positions, and with these three parameters epsilons, which sort of behave in a symmetric way. Are there any questions about this?
So those Z prime, Z double prime are coordinates of the corresponding branes, right?
Yes, intuitively, yes, right. Okay, so this was something nice that came out from our analysis, and as I said, it represents the coupling somehow or the bulk theory to these three stacks of M2 branes. For the Carl algebra, for the M5 branes, you can do something similar. There, as I said, the universal algebra is supposed to be W infinity. And now we know that the WNs, the standard W algebras, are truncations to W infinity. At first, it was quite not obvious that the algebras we define with Miroslav should also be truncations to W infinity. But then Thomas Prochazza demonstrated that by studying W infinity carefully. And also with Miroslav, they gave a very nice construction involving the coproduct. So you may remember that the WN algebras have a nice Miura construction, a free field realization, which works like this. You define this differential operator del plus Heisenberg current. You take a product of a lot of them, and then you expand it as a differential operator, and then the coefficients are generators of WN algebra. This can be generalized to W infinity by using pseudo differential operators.
So I have a question. So these algebras are represented as differential operators. Where do they act on?
Sorry, again?
Where do they act on, these differential operators?
At the moment, they're just formal differential operators. Later on, we'll actually identify them as elements. We'll identify these as an element of the tensor product of the Weil algebra, generated by Del and Z, and the vacuum module of these chiral algebras. But here I'm anticipating discussions concerning the junctions. So this coproduct defined like this for W infinity is again treats one of the epsilons different from the others. But there are actually three versions of the coproduct, three ways to present the same coproduct, which treats the epsilons in different ways. It's kind of a hidden triality. And so again, you can use this coproduct to glue together WNs in three different ways to get this WN1 and 2 and 3 in a perhaps more familiar manner. And this should represent the process of fusion of surface defects along the topological direction. Right, I should stress that when writing this picture in a sense, so here there were lines which wrap the real direction, the topological direction, and approach each other in an holomorphic direction. And that's why you get a meromorphic coproduct, which sort of depends formally on this formal parameter that describes the approach of one of the two lines. On the other hand, here we have the surfaces that wrap the holomorphic direction, but are approaching each other in the topological direction, and so you get a standard coproduct. I should immediately stress that I've only studied configurations where things wrap R or C inside the 5 directions. There are presumably other structures which emerge when you study the whole 5-dimensional geometry, but I have not looked at them. Now, after discussing the lines and their properties in fusion and the surfaces and their properties in fusion, I can discuss the junctions. So okay. How much time do I have? It was 45 minutes, 50 minutes, or?
Yeah, 50 minutes is like the 20 minutes, 20 more minutes now, at least. You know.
Okay, I might be going a little bit faster than I thought I would. You guys have not been asking enough questions, clearly. Sorry, I must be. But anyway, so I would like to discuss the junctions and their gauge invariance. So classically, gauge invariance works as follows. You have the action of some of the gauge symmetry on each defect, on the lines and on the surfaces, and this action is implemented by some currents, which for an algebra are just the Hamiltonians for the symmetry, and for the surface will be the zero mode of a current. And for a junction to be gauge invariant just means that when you act on this local operator by the sum of these gauge transformations, you get zero. And classically, this works nicely because all of these algebras are just the algebra of complex symplectomorphisms of C2, and they're Lie algebra, and the Lie algebra is a very natural coproduct in a sense. So you can write an equation like, first generator plus third generator acting on O is the same as second generator, like that. Acting on the top and from the side is equal to acting from the bottom, something like that. But quantum mechanically, all of these algebras get nonlinear corrections. And so an equation like this doesn't make sense anymore. And it requires nonlinear corrections to be compatible with the algebras themselves. And the way we decided to think about it with Miroslav was that there must be a coproduct that sends A to A tensor W, where W infinity here is the algebra of modes of the W infinity algebra. So that I can write an equation that says that T and M acting from the bottom is equal to the coproduct of T and M acting from the left, build out of the generators that come from the top and from the side. And as I said, the local operators here are live in some module for all of these algebras, and so this allows you to write down this equation. And this equation should have, a reasonably unique and nice solution which correspond to the physical junctions we know exist. If you specialize to the case where the bottom line is not there because you have a M2 brane ending on an M5 brane, then instead of the coproduct, you just need a map from the algebra to the chiral algebra to write down again an equation like this without T1, say. And in that case, you expect to find nice solutions in a context where these local operators are the product of a highest weight representation of A and a degenerate module for W infinity. Any questions? Okay. So in order to continue, we need to identify this map that will be compatible somehow with the existence of nice solutions to these equations in this context. Now, the algebra, the W infinity is known to be the same in a very non-trivial way as the affine U1 Youngian. The doubly deformed current algebra is a shifted affine U1 Youngian, and it's essentially not very naturally a subalgebra of this of the affine Youngian. So at first we thought that perhaps this map from A to W infinity could be just this natural embedding, but it doesn't work actually. There is a very interesting subtle twist, which is that the W infinity algebra has an Z2 automorphism, which flips the sign of all the odd currents. This is a very trivial automorphism from the point of view of the W algebra, but it's actually very bizarre and non-linear from the point of view of the affine Youngian. So our claim is that the correct map to use to find gauge invariant junction is the natural embedding of the Youngians followed by this Z2 automorphism. Now, one of the reasons people like to use the affine Youngian to describe W infinity is that it gives a very nice description of the degenerate modules for the W algebras, for W infinity, in terms of some nice combinatorial pictures involving stacking boxes, crystal melting, with relations to Donaldson-Thomas invariance. it's a very beautiful and rich story. Now, so we're hoping to use that story to understand this map and to understand these gauge invariant junctions. But the actual story is a little bit more interesting. So if you take these nice box counting modules and you apply this automorphism, you get a new class of conjugate modules, which have a very different combinatorial description. So here, in the standard modules, you sort of stack boxes inside a corner. I wish perhaps I should annotate. So I was supposed to have a slide that I dropped for some reason with drawing some box stacking. So in the standard modules, you have some, for example, to describe the vacuum module of the Fine-Youngian, you take a corner and you start filling it with boxes. And each configuration of boxes gives you a basis vector, and there are very simple combinatorial rules on how the generators act on these configurations of boxes.
But there are some conditions, right, on this McMahon module. So like,
right, if you want to get a degenerate module, what you do is you add some semi-infinite, columns of boxes, and then you start building on top of that. But if you apply this funny conjugation, you get a very different combinatorial description where you now have two different corners. And in this corner, you sort of stack boxes in the usual way. And the other corner, you do some more complicated stuff with boxes. There is a combinatorial description, but it's a bit more complex. But the interesting thing is that if you take generators of A inside W infinity and you start acting on the highest weight vector, you only build in here. And you don't build in the other corner. And so you get a sort of a sub-module of your degenerate module, which looks like a highest weight module for A. And you can use this to build a nice gauge invariant junction in the product of a lowest weight module A and a conjugate degenerate module for W infinity. And there are relations to the theory of Donaldson, of Vanderbal-Thomas invariance. There is a fun relation. So the partition function of Donaldson-Thomas invariance sort of count the number of configurations of boxes. And it's known that it can be written as the McMahon function times the partition function of the Vanderbal-Thomas invariance. And here you get a nice algebraic explanation of that. But the McMahon function is just the partition function of boxes in this corner. And the Vanderbal-Thomas partition function has to do with the box building in this alternative corner. I'm sorry, I'm clearly condensing a lot into.
Can you explain a bit more, like what's the connection with the junction? So like, because you have a brane and the M2 brane ends on it. So what's like, why do you have two corners?
No, so right, so the two corners sort of demonstrate that the modules of A are hidden inside the modules of W infinity.
Of W infinity in a non-trivial way with a Z2 kind of automorphism.
That's right, that's right. And so because of this, you can now take sort of the highest weight module for A with some data and tensor it with the degenerate module of the chiral algebra, again with some data. And inside here, you can try to solve this equation that the generators of A acting on this, acting here, had the same effect as the image of the generators of A acting on the right-hand side. And if you can find a solution on that, that will be a gauge invariant junction between M2 brane and M5 brane. Now, I suspect I'll have to now stop annotating or erasing. Okay, because there was a notation is going to stay there, right?
They should be clear all. Yeah, okay.
Yes, thank you. Okay, it was this. Okay, so this can be done concretely. So let me look at the case of a single M2 brane. So in that context, we have the while algebra, and we have some WN, some of these WN algebras on the fibrines. I have the highest weight module for the while algebra, which is just polynomials in a variable z, and I had the degenerate module with one box for the W infinity algebra, and you can look for a gauge invariant junction in here, and what you find that is just the vertex operator at position z. So the vertex operator at position z satisfies some interesting differential equations, which are essentially closely related to the BPZ equations, which tell you that if you act with the polynomials with the differential operators in the while algebra that realize T and M acting on Z, that has the same effect as the image, the generators which are in the image in W infinity acting on the degenerate field. And if you now look at multiple M2 branes, which involve more complicated degenerate representations and involve this Calogero representation of A, then you find a relation that tell you that the Calogero Hamiltonians acting on a product of degenerate fields has the same effect as certain generators of W infinity acting on the same product. And this explains all sort of peculiar relations between Calogero models and W algebras you can find in the literature. And using this strategy, one can build a sort of fusing elementary vertex operators. One can build gauge invariant junctions for any number of M2 branes and M5 branes. And all of these junctions are sort of automatically compatible with coproducts, so that as you fuse lines horizontally or you fuse surfaces vertically, the gauge invariant junctions combine into new gauge invariant junctions. And this gives all sorts of interesting relationships. For example, if you fuse, you can consider a situation where you have a junction from an M2 brane coming from above and one from below. This will sort of a degenerate field and a conjugate degenerate field. You can fuse them, and you actually get the Muir operator, which also operates. So that this sort of degenerate, the differential operators I was writing here, also has the property that acting with an A generator from the right is the same as acting with the coproduct of A and A, with a coproduct of that generator in A times W infinity from the left. So this Muir operator is also a gauge invariant junction. And you can, it's really fun. You can find the Muir operator by fusing two degenerate fields. And right, as I was saying, you can do a variety of other constructions. So you fuse these junctions horizontally and vertically, and they have nice interpretations within the context of in the theory of W algebras. For example, as you fuse two surfaces, making a coproduct in the chiral algebra, and you try to build junctions for this new fused configuration, say ending an M2 brane on the configuration, you can do it in two ways. You can end on the first one, or you can end on this, or you can pass through the first one and end on the second one. And the two options sort of differ by a finite segment stretched between the two. And if you stare at this long enough, you recognize that this sort of suspended M2 brane is just a screening charge for the Coulomb branch construction of W algebra. And so, staring at these pictures, you can reconstruct sort of free field realizations of a variety of things. So Yeah, so this is more or less what we did a year ago with Miroslav. Since then, we've been looking a little bit at generalizations of this. As I was saying, you can find UK or UK/K prime or D1 alpha versions of all of these statements, and sort of which end up involving things like spin calogero models and Wn plus infinity Carl algebras. But the general structure is more or less the same, just the details change and there is a bit more algebraic complications. Now, there are also generalizations that go in the direction of making this complex, this C2 into a C times C star or a C star times C star. They give you either a trigonometric or an elliptic modification of the discussion. I'm still a little confused by how these modifications end up working. If you work with C times C star, now you can think about M fibrils that either wrap C or wrap C star. And in one case, you're just studying your W infinity algebra, but wrapping C star. That's pretty intuitive. But in the other case, I think you get the Q-deformed W algebras. If you work with C star times C star, there is this very funny phenomenon that the M2 brane algebras and M5 brane algebras start looking like each other. They all look like GL1 hat. Probably because of extra dualities, which allow you to sort of exchange the role of the C stars and the R. But I've not looked at it carefully.
So we should expect trigonometric RS, right? Some three-directional or whatever, right?
Right. This sort of
the
sort of thing that comes out of the quantization of the flat connections on the torus. And I expect that a lot of the nice algebraic structures in the DIM algebra might be explained from this perspective, but I have not done so. Also, the coproducts and intertwiners presumably have a direct crystalline theory interpretation, and I think it would be nice to spell it out. And right, my goal for the future is to sort of try to figure out better how to encode this sort of information back in the bulk in terms of these factorization algebras, and ideally back to the physical theory, but that's still pretty far as a goal. Nevertheless, I think it would be very cool if somehow the theory of W front current algebras and whatnot ended up putting direct constraints on the low energy effective action of M theory. I think it is conceivable, at least. And right, I should also mention that there has been recent work by other authors on other forms of twisted M theory. There's some very recent work by Williams and Saberi, for example, on situations which are not omega deformed, and there are interesting algebras coming out too. And I think there is a lot to do in this topic, and I think it would be very great for people who really know well these algebras to give a hand. Because with Miroslav we've been doing things a little bit by hand, and I think that there must be better ways to do and to present and to organize what we've been doing. Okay, I think more or less I said all I want to say. And are there any questions?
Thank you much, Davide. Questions?
Can I ask a physics question?
Yes.
So in the kind of speculation on application to M theory, is the idea that there would be both the holomorphic sector and then kind of an anti-holomorphic sector, and then there's some kind of rough product of these, or is it really just genuinely the holomorphic sector that's supposed to lift into M theory?
I think it's just holomorphic sector. I don't know of situation you have both. I mean, I would love it would be lovely to things like a Liouville theory too, but I've not seen it appear in the Western theory setup. It might be possible if you take maybe some you know.
Well, I'm wondering in the context of, say, application of topological string to kind of supergravity couplings or something like this. Sometimes z top appears and sometimes mod z top squared appears.
No, that's right. So I think depending on the geometry, and I could imagine there is some geometry where there are two different fixed points with different orientation, and then you will end up with something holomorphic and something anti-holomorphic.
Okay, I see. Mm-hmm.
But what I was thinking about here was something more, something simpler in a sense. If in principle it should be possible to sort of, very much in principle, having an effective action for M theory with a whole bunch of higher derivative terms, it should be possible to twist it and see what comes out. And hopefully, at least some of these higher derivative terms will affect what comes out, and vice versa. Knowing what comes out might constrain at least some of these higher derivative terms, at least I hope.
Okay, so similar to like grab a photon type. Okay.
Yes, okay. That's right.
Got it. Okay, thanks.
More questions? Okay, good. So let's thank Davide. Thank you very much. So we have some more time before the next talk. So let's begin at 6 sharp. Yeah, so we can continue discussing. Yeah. Well, unless Davide is leaving.
Oh, I'm here.
So what's the new stuff that you've been doing? So you said that that's from the last year, and now we're trying to do more.
Well, so with Miroslav, we did work out some of the generalization to other toric Calabi-Yau.
Which one gives D21 alpha?
That's one. The one has. Yeah, we didn't look at that very much, but it's the one that has two legs coming in from each direction.
I mean, like it should be some fine tuning for SU2 cube, right? So like there should be some like in D21 alpha. Mm-hmm.
See, I mean, we only know how to deal with the Calabi-Yaus without inner face. But the toric diagram has no faces, no finite faces. And so those are, I believe, the only ones that exist are sort of the one that comes from SU n/m, or this exotic example. I think everything else has internal phases. And yeah, at least things seem to be roughly working. We can get Calogero-like constructions, and
so there's all these Calogero Hamiltonians that form commutative subalgebra in A, right?
Yes.
In the full A with the 3.
Yes.
Yeah. Mm-hmm.
And the main challenge is that the algebra is more complicated now. You have all sorts of GLN. Everything is matrix valued, and so it's been a little bit more painful. And I keep hoping that there will be, I can find just some math paper where I can just say, oh, okay, they already did this calculation. We don't need to. But I mean, people obviously seem to like more the elliptic version than the affine versions.
Yeah, I think it's
the rational versions. And also somehow the way we the distinction between the algebra and the chiral algebra, and the fact, they have an interplay, but they are different. They play a different role. This makes the communication more complicated. I mean, yeah, for example, I would love to know if people have studied, the interplay between these sort of different coproducts, the topological one, the meromorphic one. But typically, what I see is discussions of the coproduct for DIM.
Like DIM itself, and yeah.
Yes, which presumably capture, contains inside all of the things we've been doing as different limits.
Yes, I think also Zinkevich gave a talk yesterday, and he mentioned that there's an infinite set of coproducts, right? So is it just in DIM? Is it just in DIM, or in the whole thing? So DIM itself has like the structure of Hopf algebra is more complicated, right?
Yeah. And this, I believe, has a physical meaning, right? In the sense that you can wrap your fibrils in different slopes inside C star and C star, and you can approach them in different directions. But I mean, at least I can imagine that all these various coproducts have different geometric.
Right, so they're parameterized by the slope, right?
Yes, that's right. And
also, what about the topological holography? Like, is there anything to say here? So, as far as I understand, it's sort of one side, right? You can think of some geometric transition to.
I would love to know what is the five-dimensional geometry which is dual to the sphere partition function of M2 branes. So at the sphere partition function of M2 branes, you can do correlation functions of fixed branch operators on S3. This gives you a trace on the M2 brane algebra.
I think. Yeah.
Okay, so you don't just get an algebra, you get an algebra with a trace. This should be holographic dual to whatever is the twisted supergravity version of EDS 4 times S7. I don't know how that looks like, but in principle, that should be a five-dimensional geometry which is dual to the trace. And this doubly deformed current algebra, I believe, has a big space of traces. So this one that you get from the sphere partition function is just one specific one. And I don't know if all the traces might have an holographic description or only this one. Or I would like to understand a bit better what the role of these traces is.
I think we need to go to the next talk. Ole, are you ready? Yeah, thanks, Davide. Yeah, see you around. Ole, you can try to share your screen. Yeah, we can hear, we can see you. Hi. We do not hear you if you're saying something.
Can you hear me now?
Yeah, we can hear you now. Yes. So you should be able to share screen.
Yeah, I was just trying, but I'm logged in with two different devices, so I'm trying to share my screen with my iPad rather than my laptop here. And I did share screen, but it's not coming up at your end. So
okay, let's see. Yeah, I see it. The second user.
We'll go again. Share screen. Start. All right, I think that's.
Yeah, we see it now. Yes.
All right. Terrific.
Okay. You ready?
I'm good to go. Yes, thanks very much. And
So great.
thanks
So
for the,
yeah. So our second speaker is Warnaar from Queensland, and he'll be talking about generalized elliptic Selberg integrals.
yes, thanks very much. And it's great to well, to be able to attend this workshop. I must admit, in the last few weeks, it wasn't looking like it. So Brisbane was badly flooded, and we only got internet back on 2 days ago. So it was getting pretty tight. But anyway, here I am. So it's great to talk about some recent work that actually most of it hasn't been published yet. So this is work with Seamus Albion, former student of mine, who's now doing his PhD in Vienna, and Eric Rains at Caltech. Certainly in the elliptic community, many people know of some of Eric's work. All right, so essentially my talk is going to be in two halves. So my talk is a little bit different from the ones that I've listened to so far. So I'm not a physicist. And so perhaps it's a little bit more in the special functions and elliptic functions side of things.
None of us really are. Yeah.
Sorry?
No, never mind.
All right. So so the first half of my talk, it's essentially I'm trying to give you a small survey of very classical results where well, the aim is in the second half to give you some update on generalizations to the elliptic level, and all of this is around the Selberg integral and generalizations of that integral. So of course the Selberg integral, I hope that for most of you this is not the first time you see the Selberg integral. In any case, if it is, it's here up on my screen. And so the Selberg integral is a very classical result in special functions, and of course has many applications, including in conformal field theory. And I'll say a little bit more about that later. So it's certainly not just a pretty integral evaluation, but it's also one that's been extremely useful. It's been extremely useful. So in things like number theory and numerous other, if you're interested in hyperplane arrangements or you name it, and probably the Selberg integral has appeared. So in any case, so it's essentially a higher dimensional generalization of the Euler beta integral. So I've written it here as a k-dimensional integral, and if k is 1, this is just the Euler beta integral. And so essentially what you're doing here is you take so maybe I can highlight this here. So this part of the Selberg integral here that I just underlined, that's essentially just a k-fold Euler beta integral. So of course, to make this more interesting, you need to couple the different integration variables, and the way you do that is essentially by a power of the Vanderbal determinant. And so the power here is 2 gamma, where gamma is just some complex number. So of course, the 2 here is just for historic reasons, but it actually turns out that 2 is it's quite convenient to write a 2. Of course, I could absorb this into the gamma, would of course make the right-hand side slightly less appealing to look at. So in any case, so this is the Selberg integral, and it's quite an old result. So there's many generalizations, and so I'm going to, I guess, quickly run through a number of them because all will appear later. So the first one is a generalization. So this delta here is essentially, so let me go back to the first slide. So this delta here is just the Selberg integral, or the integrand, or the Selberg density. And now essentially we dress up that Selberg integral by some interesting symmetric functions. And the first one to do this was Cadell, quite a while ago now. And he included a Jack polynomial in the integrand. And this is in fact particularly relevant if you're interested in say conformal field theory, because as you probably also know that the Jack polynomials feature there quite heavily, in particular if you're interested in computing, well, things like conformal blocks and so on. You can often express them in terms of these types of integrals where Jack polynomials show up. So in any case, I haven't given you the right-hand side, and I'll be suppressing many of the explicit evaluations because, well, you either know what it is, otherwise it's just, again, some pretty product of gamma functions. But just for the sake of keeping it relatively simple, I've just suppressed the expression. But in any case, Cadell evaluated this integral into an expression that looks very similar to the Selberg integral, slightly more complicated because, of course, it's going to depend on the partition lambda that is labeling the Jack polynomial, but other than that, not much changes. And then there's a number of other generalizations. So what's known as the Warnaar integral, where essentially now you take two Jack polynomials, so it's slightly more complicated. Unfortunately, when Cadell did that work, so Roy essentially looked at the Schur case first, and then Cadell really did the Jack case, that the three parameters in the Selberg integral, the alpha, beta, and gamma, that beta is equal to gamma. So you can see over here that rather than a beta, he had to set beta equal to gamma, otherwise the evaluation didn't work. And it was quite a bit later that Alba, Fateev, Litvinov, and Tarnopolsky realized that what was really going on, if you want two Jack polynomials, so my notation is different here, and I'm using platistic notation. I'm not sure if everyone is familiar with this. I'll try to explain it a little bit on the next slide, but it's essentially some fancy additive notation that's very standard in the theory of symmetric functions. And the point is that if you want beta and gamma to be independent, then you have this second Jack polynomial is platistically shifted. So there's this beta over gamma minus 1 there. And well, you can all see if beta is equal to gamma, then beta over gamma minus 1, that just becomes 0. And then you have a non-platistically substituted Jack polynomial, and that is the Warnaar integral. And again, I'm not giving you what the precise evaluation is here. So especially this last integral is really being relevant, I guess, to physics. Well, because it's related to the AGT conjecture, and in particular AFLT. When they used this integral, it was to I guess to study the AGT conjecture for SU2. So that naturally led to this integral, and they had to evaluate this. So again, it's sort of a demonstration that these integrals are not just nice from a special functions point of view, but they're actually very useful if you want to do computations, for example, in conformal field theory and so on. Okay, so, well, as I said, a little bit on this platistic notation, if you haven't seen that before. So it's some sort of additive notation inside the argument of symmetric functions. So if you take the Newton power sum on variables t1 up to tk, and you add a complex variable z to it, so you should really view this z as very different to the ti's. In sort of the language of lambda rings, the TIs, they are sort of rank 1 elements, and this scalar here, or binomial element, is quite a different object. And so you can see on the right-hand side, indeed, it's treated quite differently. All of the variables of your symmetric function, your proper variable, your rank 1 elements, they're raised to a power r. That is what you usually do in a power sum symmetric function. And then this last platistically sort of z, the shift, platistic shift, you simply write it as plus z here on the right-hand side. And of course, that defines it, given that the power sums, they are an algebraic basis of the ring of symmetric functions. This, of course, implies the notation that I'm using here to express the AFLT integral. So this beta over gamma minus 1 is like your z over here. So we have a second symmetric function with a platistic shift. And I already mentioned that this AFLT integral was particularly relevant to the study of AGT, and in this case, AGT for SU2. Okay, so, all right. All right, well, so that's not the end of sort of the list of of classical things. So this goes even further back, well before Selberg was around. So this is just the hypergeometric differential equation that was already studied by Euler and by Gauss, I guess. And in particular, well, I mean, as hopefully everyone knows, this is just a differential equation with 3 regular singular points, 0, 1, and infinity. And for example, if we look at the regular point 0, and we try to solve this equation, there's of course 2 linearly independent solutions, sort of a regular one in the sense that it has exponent 1, and then another one that has exponent 1 minus c. So the simplest solution, so one of these 2 linearly independent solutions, which is really well behaved when at the origin, is this integral that was written down by Euler. So this is essentially just an integral representation for the hypergeometric function, because of course this hypergeometric differential equation, I mean, the solution are essentially the Gauss hypergeometric function. And okay, so that's what Euler did. If you take x equal to 0, well, in fact, or x equal to 1, it doesn't really matter. Of course, in this picture here, we have in the complex x plane, we should avoid 1. So let's just take x equal to 0. That Gauss hypergeometric function just trivializes to 1. Okay, so in other words, this just gives you the Euler beta integral, which is the simplest case of the Selberg integral. So the point here, that I'm trying to make is that the Euler beta integral arises as a special point if you solve this second order differential equation. Okay, so that's what I'm saying here. At f is 0, this function is 1, and it gives you the Euler beta integral. And as I said, this is just a special case of Selberg. So you can then ask yourself the question, well, what about the full Selberg integral? Is that again some special case of maybe a solution to some differential equation? And it turns out that the answer to that question is yes. And in this particular case, you need to look at the KZ equation, so the Knizhnik-Samolotchikov equation, and of course, there's many incarnations of this. So here, what we're looking at is essentially 2. So previously, in the case of Euler, of course, we were looking at an ordinary differential equation of degree 2. Of course, we can sort of essentially also view this as 2 partial differential equations of degree 1. And the more general picture is really that you need to go to the picture of partial differential equations. So that's what we have here. We have 2 partial differential equations just in 2 variables, z and w. Of course, with the KZ equations, you can do this on any number of variables, but this will be enough for us today. And essentially what we're looking at is solutions. So for this function u here, in the space of, so we take the tensor product of 2 irreducible representations. And because we were doing SU2 or SL2 here, it's just very simple representations. And now we're looking at solutions in this tensor product space of weight, well, lambda plus mu minus k times alpha 1. Okay, alpha 1 is simply the simple root of SL2. So if k is 1, you precisely get the, well, essentially Euler's solution back in a slightly different form. And if we take more general values of k, we in fact get solutions that again will give us the full Selberg integral. So as I said, one can solve this equation, and it gives, in terms of k-dimensional integrals, and this sort of classic work of Heckman and Vachenko, and at special points. So previously, when we did the Euler case, right, our special point was just sitting at the origin. Now, of course, we have 2 variables, z and w. And so at some special points, you precisely get the Selberg integral. So that's very interesting. And well, so now of course you can say, well, why should I restrict myself to SL2? So now we really understand the Selberg integral as being related to SL2, which is perhaps somewhat counterintuitive because of course the Vanderbal determinant itself, so I'm scrolling back here, of course you might say, well, that's actually related, right, to SLK here. But you can sort of attach more than one root system to this integral. And so you should really view this from the KZ point of view, this really belongs to SL2. And the KZ equations, well, it's very easy to just, the whole picture stays exactly the same, but rather than dealing with SL2, you can take just any simple Lie algebra if you wish. But for us today, it's enough to just consider rather than SLN, now, in fact, it's slightly more convenient to take SLN plus 1. So that's what I'll be doing. And it's still the solution of Heckman and Varchenko, in fact, worked for any simple Lie algebra. So we can certainly also take SLN plus 1 here. And this leads to integrals that are higher dimensional generalizations of the Selberg integral. And well, it turns out, so this is now going to be a lot harder. This picture doesn't actually give us evaluations of these integrals. So in the case considered by Euler, all we had to do is take a solution and take a special point, and immediately a nice evaluation popped out. That's no longer the case here. But it turns out that these integrals at the right points are, in fact, you can actually evaluate them into closed form. And that's what I'm going to try to describe to you next. And unsurprisingly, what I'm going to describe to you next has a strong representation theoretic flavor. After all, we started with, right, partial differential equations in the tensor product of two irreducible representations. So clearly, whatever we're getting out should have some representation theoretic interpretation. And so I'll explain that in a moment. So for now, I'm just going to try to explain to you what the structure is. So I take, so n integers, and well, they're all non-negative, and I need to strictly order these integers. Okay, so I have a k1 that is less than or equal to k2 and so on. And then for each of these integers, so essentially what you should do is k1, you should associate that with the first vertex of the AN Dinkin diagram. And then we have a k2, there's a second set of variables that is associated to the second vertex of the Dinkin diagram. So each vertex now contains a set of integration variables, and the number of integration variables attached to each of these vertices. Well, the first one, there's k1 integration variables. The second one has k. So for example, if I go over here, right, there's k3 integration variables. So that's where that k3 belongs to, and so on up to the last vertex. And of course, that's kn. And then as before, so in the case of Selberg, of course, we are just looking at the A1 Dinkin diagram. So you only had one set of variables. There was only a single k. And so to each of these sets of variables, you're going to integrate over a Vandermonde raised to a particular power as before. So that's just this delta t here is just a Vandermonde of a set of variables t. But we also need to have something that represents the edges of my Dinkin diagram. So if I have two consecutive alphabets like T1 and T2 or T2 and T3 and so on, then the right thing to do, sort of the generalized Vandermonde in that case, is just taking the product over the difference of all of the integration variables in the respective sets of variables. So here like Si minus Tj's running over all I and all J. Okay, so these are the ingredients that we need. And so this looks like something very, very complicated, but let's try to unpack it. So as before, we have some sort of beta type integral expressions in each of the variables that we're integrating over. And then we have, for each set of variables, we have a Vandermonde raised to the same power 2 gamma as before. But this Vandermonde type product for 2 consecutive vertices on the Dinkin diagram, you now see the 2 becomes a -1. And of course, so that's why I said earlier, the 2 was actually a very fortunate choice, because the 2 and the -1 that you're seeing here, they're precisely the Cartan integers. So if you had considered the more general type, well, just any simple Lie algebra, then of course it would not have been 2 and -1. Well, it would always have been 2. That's just along the main diagonal. But the off diagonal exponents, of course, it would have depended on the particular Cartan integers for whatever type you were considering. Okay, and as it turns out, well, this is, I mean, the precise form is not that important, but you can see we have a closed form expression in terms of gamma functions. But there's something we need to do here that's worth noting, because that's really explains the connection to representation theory. So I said this first top line here. So again, I was sort of looking at this bit here, that these were essentially beta integral factors. So TI's raised to the powers alphas and 1 minus T's raised to the powers betas and so on. But we need to take all of these betas to be equal to 1, except for the last one. And the alphas can be completely arbitrary. So I'll explain in a moment why that is. Let me just first say that for SL3, this integral was first written down by Tarasov and Varchenko as a solution, indeed, or in relation to the KZ equation. And then a little bit later, I computed this full integral, not really using KZ methodology to prove this, but Macdonald polynomial theory. Okay, so what's going on here? So where's the representation theory? If you just see this integral for the first time, it's not clear that there's a lot of representation theory structure in it. So let's maybe go back to the picture coming from the KZ equation. So as I said, we're working in the tensor product of 2 irreducible representations. So that's the same if you're working in general type A. That's what we're doing. Now, the prediction is, so if you take solutions in that space, so you of particular weight, so if you take in general, if you take a tensor product of 2 irreducible representations, as we all know, we can decompose this into irreducibles. And what you really want is that in this decomposition, so the particular weights that you should focus on, for which you expect to get nice closed form evaluations, you want these to be precisely weighted such that the multiplicity in this tensor product decomposition is 1. So that's a very strong restriction. In fact, Mugen and Varchenko, they conjectured that in general for Selberg integrals of type G, that whenever you sit in such a point of multiplicity where the tensor product decomposition has a multiplicity 1, that for those weights, you would get a nice closed form expression. And so this integral that I was just showing you is one such example. And so maybe on a bit of scratch paper, I can try to explain what that is. So as I said, you need to take 2 representations. Okay, so in general, we have something like this. We take the tensor product. We try to decompose this. And so let's just write it like this. And of course, we get some multiplicities on type sort of GLN. Oops, that's not how I want to write that. These are essentially nothing but the Littlewood-Richardson coefficients. Okay, so what we really want, we want this. We want to take weights nu here and also perhaps fine tune our choice of lambda and mu so that this comes out to be 1. And then the prediction is you should get a nice integral evaluation. And so in one particularly nice case is when you take lambda to be completely arbitrary. So I'll just now write the weights. I think physicists do this a lot like that. And for mu, I just take a multiple of, say, the first fundamental weight. It's well known that if you take something like this, that it decomposes. In fact, this is completely multiplicity free if you do the decomposition. And what do you get on the other side? Well, you get, for example, this weight showing up in the decomposition, plus, if you wish, lower weights, where essentially what you're doing, you're subtracting things of this form. So what you're going to subtract is a linear combination of alpha 1 up to alpha n, they're just the simple roots. And these KIs are precisely the cardinalities of our sets of integration variables that I was considering previously. And it turns out if you do this decomposition, then you precisely find, well, in fact, in this case, I really what I'm doing, because it's rather than 1 here, I actually take n by duality, just a Z2 automorphism of the Dinkin diagram that is going to give me the same. And then this precisely corresponds to the only, if you do this tensor product decomposition, it just tells you that the only weights you're actually getting are weights for which these KIs are ordered. So that's where that was coming from. And similarly with the actual exponents in the integral, oops, it's of course not going to work here. I need to get back to the integral. These exponents, alpha and beta, they are also related to your choice of weights. So for example, the alpha I are nothing but, well, I should say proportional to things like your lambda. And well, now it's very unfortunate because these alpha i's here, they are not the alphas in the Selberg integral. So maybe I should use a different color. It's still going to be confusing. So this is my exponent alpha in the Selberg integral. It's very unfortunate that that's traditionally written as an alpha. And of course, alphas for simple roots are also written as alphas. So in any case, things like that. And so again, if you take special weights like this, then it turns out that most of these exponents are just going to be 0 or 1, I should say, which is why a lot of these betas, well, 0 indeed, and that's why these betas must be 1. So this particular choice here and the ordering of the KI, that's all just dictated by the representation theory. In any case, this is what it is. And similarly, you can throw in some extra Jack polynomials and you still get a nice closed form evaluation. So you can, in particular, have an AN version of this AFLT integral. All right. So now finally back to SL2. And one of the, I guess, very first results in the theory of sort of elliptic hypergeometric integrals is this elliptic version of the actual Selberg integral. So this was conjectured by, well, Slava here together with Van Dien. Slava had earlier the K is 1 case, so the elliptic beta integral, he had proved that. And then together with Van Dien, they conjectured this integral evaluation, where now the gamma is not your previous standard classical gamma function. From now on, all my gammas are going to be elliptic gamma functions, which I'm not even going to define for you. But nonetheless, this integral can be shown to be a perfect analog of the classical Selberg integral. So it was in fact shown by Eric Rains that by taking precise limits, you do get back the actual Selberg integral. And so as I already mentioned this, so in the case K1, that is the elliptic beta integral by Slava, and then for general values of K, this was conjectured by Van Die and Spiridonov, first proved by Eric Rains in his famous Annals paper, and subsequently others proved it as well. Slava has some really neat short proofs of these types of integrals, and Ito and Naomi much later had yet other proofs, and maybe there's others that I've missed, but in any case, we are quite good nowadays with evaluating integrals of this particular type, and we have a number of methods that we can apply. So the sort of two main questions, I guess, for the second half of my talk is, well, can you, in this, for example, just SL2 Selberg integral, can we include analogs of Jack polynomials? So for example, can we bump this up to something like an elliptic AFLT integral? And then of course, if we are more ambitious, we can say, well, can we even do this in the general AN case? Okay, so that's sort of the questions that Eric Rains and Seamus Albion and myself, we asked ourselves, can we do this? Okay, so before I get to that, are there any questions about this classical story? It's probably a good moment to pause. If there are no questions, then I'll continue. All right, so first of all, when we want to sort of include symmetric functions in the integrand, the first question we really have to ask is, well, what is going to play the role of the Jack polynomial if we go to the elliptic level? And that's a story that is well, that's certainly a question that's been studied quite extensively and we understand really, really well. And so that's the interpolation, the BCN symmetric interpolation functions of Rains and Koskun Gustafsson. So they were discovered independently. I guess the only perhaps surprise, if you're relatively new to these kind of things, is that the Jack polynomial is, of course, a symmetric function. So it has, well, because I work with K variables, it has SK symmetry. But these at the elliptic level, we really have to go to BCN, or perhaps BCK would have been more precise if I'd written that here. So at this stage, we don't have sort of the elliptic analogs of type A. We really have to go to type C or BC. But nonetheless, in the limits, I mean, that's something you can already see in the elliptic Selberg integral. I mean, I didn't even explain the notation here, and perhaps I should have. You see all these Z plus or minus 1 or plus or minus, and what that really means is you take a term either with the plus exponent plus 1, and you also take that same term with an exponent minus 1. So in other words, this integrand here of the elliptic Selberg integral already has that symmetry that if you replace any of the Z variables by its reciprocal, nothing happens. And of course, we still have SK symmetry. So if I replace Z1 by interchange that with Z2, then this integrand is invariant. So again, this has BCN or CN type symmetry rather than type A or symmetric group symmetry only. But nonetheless, in the appropriate limit, this does reduce back to something of type A or SLN. So that's quite tricky how to do that, but in any case.
Is it some sort of scaling limit? You need to scale some
Well, you didn't need to. So yeah, there's a Eric Rains calls this, there's a symmetry breaking trick. Because of course, if you take a limit in a naive way here, you're never going to get rid of your hyperoctahedral symmetry. That's really what it is. So you somehow need to favor maybe the plus over the minus and so on. So so yeah, there's a bit of a trick to do that. It becomes quite technical, but in any case, I say we know how to do this. It was really Eric Rains who very precisely showed how to do this. And so that indeed breaks that symmetry. It doesn't break the SK symmetry, but it loses the extra hyperoctahedral bit. So the reciprocal, replacing a variable by its reciprocal, that symmetry is no longer there. So yeah, so that's the same here in this more general story. We start with a Jack polynomial, but now we go to some BCN symmetric functions. They're no longer polynomials. I mean, that's pretty clear because we're dealing with elliptic functions here. And these functions, they're in the non-elliptic case, they're Okunkov's BCN symmetric Macdonald polynomials or Macdonald's interpolation polynomials. So if you're familiar with that, these functions that were found by Rains and Koskun-Gustafsson are essentially elliptic generalizations of those. And I don't have time to properly describe these functions, but I mean, why are they interpolation functions? So, I mean, here I've written one down for you. So depends on n variables. Later that n is going to be k again. Some extra parameters, then a t and a p and a q. And they're indexed rather than by partitions, which is what you're used to in symmetric function theory. They're indexed by bipartitions. So it's just a pair of partitions. And then they have really nice vanishing properties. So if you take all of these variables, you take xi and you evaluate this essentially at another partition. So I take another bipartition lambda, and I take p to the lambda, essentially the ith part, and then q to the second partition in this bipartition, also to the ith part, and I stick that in here, and I do this for all of the n variables, then you get vanishing. Okay, so it vanishes at all these points for which your bipartition lambda, so there's a sense of containment, just like you have for ordinary partitions. You can extend this to bipartitions. And so whenever the partition mu is not strictly contained, or is not, I shouldn't say strictly, is not contained in the bipartition lambda, then this function vanishes. Okay, so that's sort of the interpolation structure of these. And it's very similar, as I said, for those who are familiar with Okunkov's interpolation polynomials, he has very similar vanishing properties. Okay.
So I guess if you impose some additional constraints on Q and P, you can have a solid partition, like a plane partition. Is that right?
I would not think of this as anything to do with plane partitions. It's just a bipartition. You just have two partitions. Essentially where that comes from is this whole theory is completely symmetric in P and Q. So P is usually what we think of as the elliptic parameter, and Q is something you already have, maybe not classically, but certainly in the basic hyper or Q hypergeometric world. So in the rational world, if you wish. But it turns out if you go up to the elliptic level, so you introduce an additional parameter P, like the norm of your elliptic function, then somehow you can make things completely symmetric.
So you should not expect any McMahon kind of modules, right? It's not the place to look for them.
I don't think so. I know, I don't think that would be related to anything like this. And so, yeah. So here you can just see, for example, if you look at these interpolation points, so if I take P to be 0, which is essentially the rational limit, so I'm no longer in the elliptic world, you can see that the first partition of this bipartition, lambda, it completely disappears from the picture. The interpolation points are now only Q to evaluated with exponents being some partition. So rather than now bipartitions, in that case, you're just dealing with ordinary partitions. And it also turns out this function R of mu itself, if you set P equal to 0, the first partition in the bipartition just completely disappears, or the dependence on that partition disappears. And this just becomes a more traditional, well, essentially just becomes Okunkov's BCN interpolation polynomial, which depends on a single partition. But I don't really think there's a McMahon picture in here.
Davide, did you want to say something? You raised your hand.
Okay, so in any case, was there another question or?
So here elliptic function just means, again, this is double product of P to the N.
Yeah, that's right. As I said, I thought this is sort of late in the workshop, but maybe no one defined, for example, the elliptic gamma function, which is indeed precisely what you're saying, indeed, the double product. So I apologize. I mean, I'm not defining many things because otherwise it just takes too long. I was hoping that most
No,
people.
I just want to know if this was the same general thing as the gamma, not say theta function.
Yes.
Yes, so we have a talk by Shlomo Razamar. He defined them all earlier today.
Okay, well,
Really
terrific.
yeah.
Unfortunately, I could not. I think that was in the middle of the night for me, so I skipped that. So in any case, so if you recall Shlomo's talk, then yes, I'm using hopefully exactly the same notation. All right, let's move on. So that was just this function just plays the role of the Jack polynomial, but there's a complication. Because if we want this AFLT type integrals, then we had two Jack polynomials, but one was platistically substituted. Now, these platistic substitutions really do not work in type BCN, because it's really your need to work in the ring of symmetric functions in infinitely many variables. That is really, you need to interpret that as a lambda ring and essentially of a single element, and you can make sense of what platistic really means. And platistic substitutions. In type BCN, that is just, it no longer works. So that's a little bit complicated. So the question then is, what plays the role of platistic substitutions? And again, I have no time to really explain how one can solve this, but essentially all I'll be saying here is that there is a slightly more complicated interpolation function. So it depends on, well, I've just chosen the simplest case on two extra variables that are going to play the role of a platistic shift. You can do this more generally with any number of extra variables. For us, it's enough to do two. And in particular, so all the stuff here colored yellow, you should really think of that is a platistic shift. And in particular, I've shown you this more complicated interpolation function, and I see I'm missing, so for whatever reasons, they have a star when they are defined. In the limit, you can see that here I've taken this function and you see some gamma and beta in there. If you take the P to 0 limit and Q to 1 limit, so that's really the classical limit, you precisely get the Jack polynomials. You can see because P is disappeared, you see only the second one of the two bipartitions has survived, and you precisely get the Jack polynomial with the appropriate platistic shift. So this is really the function we need. So to describe it in full and how one can come up with a function like this, it's a long story, so I'm just going to leave that for now. But in any case, the good news is we have exactly the functions that we think that we need. And so here is our first, I guess, theorem with Seamus and Eric. So it's the same elliptic Selberg integral of Slava and Van Dien and Eric Reins. But now additionally, you see two of these interpolation functions. The second one has these two extra variables, that's the platistic shift. And again, just for the sake of simplicity, I'm not giving you the right-hand side. It's very similar to the right-hand side that Slava Van der wrote down just slightly more complicated because it also depends on this bipartition lambda mu, but it's a complete product in terms of elliptic gamma functions. So the precise form is not that important, but it certainly has a very nice product form. So that's our first result. And then of course, well, that leads to, can we extend this to general type A? Well, okay, so I should maybe, I'm getting ahead of myself. So indeed, in the classical limit, this gives you back the AFLT integral, so that's good. You can also take a McDonald polynomial limit. So again, you're losing BCN symmetry, but we still just have SK symmetry. And so unsurprisingly, you get an integral over a pair of McDonald polynomials where the second one again is statistically shifted. And then for those who are familiar with McDonald theory, I mean, this is the general sort of kernel if you do McDonald polynomial theory. So for example, if you take two McDonald polynomials, they are going to be orthogonal with respect to this. But of course, there's a little bit extra stuff in the integrand. So this term here, you should really think of this as coming from the beta integral. So you see an A and a B in there, and they roughly play the role of the exponents alpha and beta in the classical Selberg integral. And again, this is just some nice infinite product. Now, of course, no longer depending on P. So this is just a usual infinite product in the theory of say Q series or basic hypergeometric functions. And then there's some constraints on the variables to make this integral well defined. So, okay. Anyway, so that's the SL2 case. So this is a result that we haven't yet published. So this is our second theorem. So I put a date of 2022, but I'm not exactly sure when it's going to be. So, well, to make this or palatable, I've tried to give you the structure of this integral. So like before, we have the Dinkin diagram. And we have a set of integration variables for every vertex of the Dinkin diagram. So that's no different. So that's the alphabet Z1 up to Zn. So they each are a set of integration variables. And again, there's a K1 less than or equal to K2 and so on. So again, we have an ordering. If you go to the right of the Dinkin diagram, then you get more and more integration variables. So the role of the Vanderbal determinant, we call this delta V really for vertex. That's essentially the kind of integrand that was already present in the elliptic Selberg integral of Slava and Van Dien. Okay, so that's this kind of thing. The only thing I've done is I allow for an arbitrary number of variables, TIs. And then we need, again, some Vanderbal type coupling. And of course, I completely wrote that down incorrectly here because I have Z and I don't have a W here. So let me fix that. Now it makes more sense. So this plays the role of the second type of Vanderbal determinant. So we put an E here for edge. It represents the edge of the Dinkin diagram. So you get one for each edge of the Dinkin diagram and so on. And then finally, for a little bit of structure, so I said the general integrand of this AN elliptic Selberg integral, it's going to depend on 2n+4 parameters. So in the SL2 case, that's exactly 6. So it just goes up with the rank in an even manner. And then all of these vertex deltas, so the final one contains exactly 6 of these integration or 6 of these parameters, like in the SL2 elliptic Selberg integral, but all of the other Vanderbal determinants, they only contain 4 rather than 6 parameters. So they're not quite as general as the one at the very end, which is somewhat disappointing, but we understand where that comes from. Otherwise, the proof simply doesn't work. And again, it has a representation theoretic meaning, but I have no time to explain that here. And then here's the integral. And it's completely unimportant that you look at the right-hand side, but I thought I've been suppressing these things throughout my talk. And in case you sort of disbelieve that we have evaluated anything. So just a very big product of elliptic gamma functions. But that's where it is. And you have a bunch of balancing conditions and so on. So this is now for n is 1, this is the elliptic Selberg integral, and for n greater than 1, this is a generalization to more general type A. Okay. Well, then finally, we can also again include 2 of these interpolation functions. I'm certainly not going to show you the evaluation here because it would fill up several pages, but it's just a more complicated product of gamma functions. And of course, every talk should contain a proof. So the proof is rather difficult in the sense it uses a gadget that was developed by Eric Rains a number of years ago, which is known as the elliptic interpolation kernel, which is rather a complicated beast to get your head around. It's very, I find at least, Eric's paper where he defines this function extremely difficult to read. But in any case, that's what we use. And then this interpolation kernel satisfies really nice, what Eric calls braid relations. So it has a somewhat Yang-Baxter feel to it, if you know what that is, to actually prove this AN elliptic Selberg integral. So that's really quite nice. The technique for proving these things is quite elegant once you get your head around these interpolation kernels, and I'm certainly not going to describe them here. So my time is up, so I should just leave you with some questions. So the first one, even just for SL2, is there a connection, given that this AFLT integral was really used to study, for example, AGT for SU2, well, we have a perfect and elliptic analog of it. It should have some connection to elliptic AGT. But of course, we're 3 mathematicians and we really don't understand the physics behind AGT. So maybe, of course, I mean, this is the perfect audience here. Maybe it's obvious to you how this result could be used. It's not to us. Then a really nice thing is again, just for SL2. So the elliptic Selberg integral, it contains 6 parameters, T1 up to T6. And it turns out if you add an additional 2 variables to it, it no longer has an integral evaluation, but there's a really nice transformations going on that actually have E7 symmetry. And so question is, if we go back to our integral here, and we again at this last node, rather than 6 of these T variables or parameters, we take 8, should we get an integral that has maybe again E7 symmetry or some generalization thereof? We don't yet know. I mean, we suspect that something is going on. It would really be nice to again see things like E7 show up here, but we don't have any answer to that question. And then coming back to how the AN Selberg integral originally arose, as I said, as sort of special points in the solutions of KZ equations. How about the elliptic case? Again, even for SL2, we really don't understand this very well at all. There's certainly some elliptic Selberg integrals or elliptic beta type integrals that are related to elliptic, I guess, versions of KZ, but they don't have BCN symmetry. It just stays within type A. So that's certainly not the right thing. And again, we don't know if there's a nice PDE description of some of the integrals that we've been studying. And that's probably where I should leave it. So thanks very much.
Okay, thank you very much, Ole. Questions, please.
May I ask a question? Do you hear?
Yes, I can. How are you?
This is Naomi. Hi.
Yes, good to see
Very
you.
nice talk.
I'm glad I mentioned your name. I hadn't realized that, yeah, you would be here today.
Yeah, okay. I have two questions. And one is about, you mentioned about the trigonometric limits
Yes.
to the McDonald A-type case.
Yes.
But I guess there is a natural trigonometric limit to the BCK case, right?
Well,
Okonkov interpolation function.
So now we're even just talking in the SL2 case, just the original.
Yes.
If I take the, okay, so let's.
So SL2 or SRN, it doesn't matter.
Yeah,
but BCK,
even just for
BCK limit,
this particular
trigonometric
integral,
BCK limit. Yeah.
The rational limit here. Yeah, we haven't, I mean, it's a good question. Somehow the BCN theory of Okunkov,
Yeah.
it's never really written in terms of integrals. And we don't, for example, have a weight function with respect to which they're orthogonal. They're really interpolation functions.
Oh,
so
yes.
Of course, we're used to McDonald theory where they're orthogonal polynomials.
Right.
But in this interpolation picture, these things are not orthogonal polynomials. So we know how to take a limit from this, but indeed, because we break the symmetry, the limit goes away from being interpolation type, and you go to the actual symmetric function theory. So you get indeed McDonald. And then indeed, you see precisely the McDonald weight function showing up and so on. Now, if you want to do, so yeah, so I mean, we haven't even tried, but it's highly unlikely that anything good will happen. Maybe that limit is just too singular and nothing will come out of it. After all, it would be counterintuitive if that limit would actually be meaningful.
Okay, another question. So you referred to the range, I would say, range elliptic.
The interpolation kernel.
Kernel and also the braid relation. So when you saying braid relation, it's a braid relation for integral operators or some of the kind of braid relations.
Well, so there is this interpolation kernel. It satisfies a relation. I think Eric writes it as. So these are.
There's a braid relation, the Baslava of the integral in the form of the integral operators, right?
It's not in terms of, well, these interpolation kernels are extremely difficult because you need to, the way Eric first introduces them, they're sort of formal objects. And so he talks about formal differential operators, for example. But of course, everything we're doing here is analytic. So there is a way to make these things analytic. But I believe that when you take that limit to become a proper function in the sense that you and I would think of functions that you can integrate over and so on, I think you can't take limits in these formal differential operators so well. So I really don't know what happens at that particular level with any differential operators. So there are differential operators, but I only know of them at the formal level. And yeah, so.
Okay, thank you very much. Okay, that's sufficient.
Thanks.
Thank you. Other questions? Okay, so just right on time. Thanks a lot for informative talk, Ole. Jonathan, are you ready?
Hi. Yeah, I can try going. Let me see if I can share screen. While I'm doing that, personally say thanks to Peter for the invitation to come to this and to give a talk. So it looks okay?
Yeah, it looks good.
Okay, great. So thanks again for the invitation to come and also for staying up, whatever your time zone is, I guess. I'm probably going to be on the more physics side than some of the other speakers. So I'll try to provide some motivation and what I'll be talking about. But the idea is to link together various kinds of physics topics involving so-called SCFTs, superconformal field theories. And I'm going to be discussing them in the context of 6 dimensions, 4 dimensions, and a kind of generalization of a quiver gauge theory I'll refer to as having what's known as a quiver with conformal matter, and how all of this is related to spin chains. So that's going to be my point of contact with the main theme of this workshop. So it's based on 2 papers which have already appeared, and one which will hopefully appear in the near term. So the first paper was written with Florent Baum and Craig Laurie. We're both, so Florent is a visiting postdoc at UPenn, and Craig at the time was a postdoc at UPenn. This was a follow-up that came out shortly afterwards, and we've been working on kind of the follow-up for about 1.5 years now, I guess. What's that?
Oh, sorry, never mind.
Yeah, since Corona, yeah. So in fact, Florent we wrote this paper before Florent, I think, had actually even visited Penn. He was supposed to visit earlier, but then anyway, he's here now. Yeah, and anyway, so this one got it delayed, you might say because of Corona, or because there were also things we didn't understand about what was going on. So hopefully, I think we've resolved most of the issues though, so hopefully it'll be out soon. Okay, so what I'm going to do is first of all explain kind of the general physical intuition for why a spin chain should be appearing in the first place. And so the idea is that 60 CFTs, SCFTs, look quite a bit like one-dimensional systems. And I'll explain why that is. And the one-dimensional systems here have, if we treat them as quantum mechanical systems, have quantum mechanical states. And these tell us about operators in the 6-dimensional setting. Okay, so here's the outline of what I'll try to cover. First, I'll say, why would you want to study 60 CFTs in the first place? We'll see that the structure of these things looks quite a bit like a one-dimensional system, and this will connect us up to spin chains. And then basically we'll show that certain classes of states or operators in these systems really can be described by a one-dimensional spin chain, integrable spin chain. And then I'll conclude. Okay, so why would you study 60 CFTs? So I have to tell you what these are in the first place. So what is a 60 SCFT? This is a physical theory that lives in 5 spatial dimensions and 1 time dimension. And it has the following conformal symmetries, SO6, 2, which includes the Lorentz symmetries that physicists will talk about in the context of a 5+1 dimensional theory, plus a few more. And kind of the crucial one for conformal invariance is really about scaling, namely this notion of having scale invariance with respect to the physical properties. So there's no length scales or mass scales, but there are notions of relative positions and angles, of course. So why are they interesting? So from a physical point of view, they're quite interesting because it's definitely not obvious that such 60 SCFTs actually exist. So it was actually a long-standing question about whether they existed in the first place. So do they exist? So they don't exist in the context of perturbations of what we refer to as free field theories or Gaussian fixed points. So let me just quickly sketch the reason for that. And please interrupt me at any time. I mean, I'm sure this is maybe a bit physics heavy for the crowd here, but so please stop me to clarify things. So in this context, we can write down a Lagrangian. And the free field theory limit corresponds to just talking about a kinetic term for a scalar field like this, so d phi squared, and then we can perturb it in various ways. And this is basically what we do in any textbook quantum field theory analysis of a quantum field theory. Now, if you try and perturb in 6 dimensions, the first thing you might try to add is a cubic potential, but this is unbounded from below, and it does not serve, therefore, as a good way to define what we would mean by the ground state of the system. And if you try to add phi to the 4th, this works fine. Well, it almost works fine in 4 dimensions or lower, but in 6 dimensions, it's what we would refer to as an irrelevant operator. As we go to long distances, the strength of this interaction becomes weaker and weaker. So unless we kind of tune the coupling constant in front of this potential to be extremely large, it does nothing at long distances. Okay, so on the other hand, from string theory constructions, the expectation is that yes, there are such systems, And we can construct them by basically taking various limits in which most of the stringy excitations decouple from the system. So these are theories that have a local stress energy tensor, and we basically take a scaling limit where all distance scales and mass scales disappear. Okay, so how do we construct these things? So we're talking about string theory, and basically the only tool we have to kind of control kind of strong coupling effect involves supersymmetry. And so just to remind you, we have some supersymmetry algebra involving anti-commutators of so-called supercharges, giving us translations in the 6-dimensional spacetime. And in the context of a 6-dimensional SCFT, there are basically two choices. One where we have 8 degrees of freedom for the Qs, and these are referred to as the 1, 0 theories, and those that where we have 16 Qs, and then we refer to these as the 2, 0 theories. And basically that's it for interacting theories. So are they interesting? So you can classify the superconformal algebras. So this is just an exercise in just writing down possible super Lie algebras that have the appropriate bosonic subset of generators. And as Nam showed in the 1970s, these can only exist for space-time dimensions less than or equal to 6. But the explicit examples were not found until the 1990s. And basically, it's still true that the only examples where we can directly construct the theory in the first place involve input from kind of string theory type constructions. And in all the examples that we know of, what we also find is that the theories are always quote unquote non-Lagrangian, in the sense that they don't arise from perturbations of a Gaussian field theory or a weakly coupled fixed point. So it's very difficult to study these theories for that reason. All the techniques that we usually use as physicists from kind of textbook quantum field theory courses don't work in this context. And from this point of view, it's difficult to calculate anything because we don't even know the operators necessarily, and we don't know how to compute correlation functions between those operators. So in the context of, say, like a 2-dimensional conformal field theory, you also often don't need to talk about a Lagrangian, and you just write down the operators and correlators. But we at least have many examples where we can get close to a good description using, say, free field limits, or even describe things in terms of generalized free field models. Not so in 6 dimensions. So they're interesting systems precisely because it's hard to calculate anything in them. And yet we know that they exist from various string theory points of view. Okay, so again, it's also important because the textbook definition of quantum field theory that we typically talk about does not apply in this context. So it's a major issue to even define what we mean by, in physical terms, quantum field theory. So writing down examples and writing down kind of what we know about such theories provides us more clues as to what we actually mean as physicists by quantum field theory. Okay, so that's kind of the motivation for why I'll be interested in 6D SCFTs. Maybe I'll first ask if there's any questions about my motivation. Okay, then I'll move on to some first examples. So these are kind of the celebrated 2, 0 theories. And let me explain. So these are sometimes referred to, I think, in the math literature as theory X in 6 dimensions. And this is how you build them in string theory. You consider these sources in M theory that Davide already mentioned, involving a so-called M5 brane. So these have 5 spatial directions and 1 time direction. And you take them to be parallel to one another. And in between 2 such M5 branes, you can have a M2 brane that has 2 spatial directions. You can stretch between the M5 branes. And on the M5 brane world volume, it has a common circle. This looks like a string-like excitation on the world volume of the M5 brane. And if you bring these on top of each other, this is a limit where the distance, this length scale of the size of the M2 brane, which is being stretched, has collapsed to 0 size. And in this limit, one expects to pick up a conformal field theory limit. So in fact, you can classify all the 2, 0 theories, not so much from M5 branes, that provides a way of building some examples, but actually from taking type 2B string theory on an ADE singularity. So the point is that there's an ADE classification of finite subgroups of SU2, and this is basically the entire list of known 2, 0 theories. Now, it might be possible to build another one, but nobody knows how to do it. So this is basically the sense in which we've classified. We know it's classified. These are the only backgrounds preserving the correct amount of supersymmetry, and there's nothing else. So these are all of the 2, 0 theories. And just to remind you, you can resolve the singularity, and it has this kind of form in terms of a configuration of spheres intersecting according to certain -2 curves. And we see the Dinkin diagram of the ADE type. Okay. Now for 1, 0 theories, the situation is significantly looser in terms of the constraints because we have less supersymmetry constraining what happens. And in 6-dimensional supersymmetry, we have various kinds of representations according to the supersymmetry algebra. Here, I'll just list a few of them: so-called vector multiplet, hypermultiplet, and tensor multiplet. Vector multiplet should be thought of as like the analog of a photon or gluon, and it is a force carrier, if you like. Hypermultiplet is kind of one of the matter fields that's charged under the force carrier. And then the tensor multiplet should be thought of as kind of taking one of the coupling constants of this gauge theory, controlling the strength of interactions between the photons and gluons and so on, and promoting it itself to a dynamical object, to a dynamical field. This is a characteristic primarily in 6 dimensions. It does not occur in the same way in 4 dimensions. It's really crucial in 6 dimensions to even define the theory properly, or define such 60 supersymmetric theories in the first place. Okay, so here's an example. We can consider a quiver gauge theory with various kinds of SUK gauge theory. So the circles here are just nodes in a quiver. These links here are the hypermultiplets. And so the hypermultiplets transform, you can think of it as morphisms going between a vector space, say in the fundamental representation here, and to another one in the fundamental representation here, and so on. Now, to actually get to the 60 CFT limit, what we do is we take these T's here, there's a T for each one of these circles, and we take a limit where the gauge coupling, which goes as 1 over G squared, is going to this limit 0. So G is going to infinity, formally speaking. So this is a very strong coupled limit. And this is part of the reason why it's so difficult to study these systems, because we don't really have a standard kind of perturbative expansion available to us. So this is what it looks like in terms of those M5 branes I mentioned earlier. You can consider another ADE singularity. This ADE singularity is actually, this A-type singularity is not actually responsible for building the CFT. Rather, it builds the 7D super Yang-Mills theory in this context. And what we find is when we put the M5 branes in is we get a collection of domain walls. And each one of these domain walls, so these fill out 6 dimensions inside of the 7D spacetime, each domain wall is really building out one of these links inside of the quiver. And so this finite interval piece here is associated with the SUK gauge theory. So it's really a 6-dimensional system because this is a finite interval. So if we go to long distances, then it just looks like these green pieces are collapsing on top of each other. And we have this kind of quiver that looks like this. The CFT limit corresponds to taking all of those little domain walls and putting them on top of each other. And so what's happening is that the length of the interval, each of these intervals goes like 1 over the gauge coupling squared. And in the formally infinite limit for this gauge coupling, all those lengths collapse to 0 size, and we're left with something on the left and the right for an SUK symmetry. This is now what's called a global symmetry. It's not a gauge symmetry. So this is the limit we're taking of that quiver in order to produce the quiver gauge theory in 6 dimensions, to produce the SCFT. And in this limit, we can't really rely on the gauge theory description, or it's practically, in practical terms, it's almost useless because the gauge coupling has become so strong. And you can generalize this. So for example, instead of having an A-type singularity, you can consider M5 branes probing a more general ADE-type singularity. And when we do this, we again have now a gauge group G. This could be of SU, SO, or E6, 7, or 8 type. And then we again put the M5 brane here. And now we have a link going between, say, E6 and E6, or yeah, E6 is all across. And we can think about the M5 brane as defining some kind of strongly coupled analog of the hypermultiplet, where it's still a morphism between, say, the fundamental representation here and the fundamental representation here, but it's not necessarily a weakly coupled state as it was before in the case of the SUK gauge theories. So again, you can take all the M5 branes here and pile them on top of each other, and that's the SCFT limit. Okay. Now, an issue, at least in physical terms, is that the link here is not described by kind of what we would think of as like a standard quiver gauge theory type object. It's not a weakly coupled field or a hypermultiplet in the usual sense. So what is this thing? These links here are what we refer to as a so-called quiver, conformal matter, because it's some kind of conformal generalization or CFT generalization of what we mean by a link field in a quiver gauge theory setting. So just to set up the stage, how do we get these things in general? We imagine for SUK that we have some stack of D branes, and on these we can have open strings which end. And these open strings can literally be thought of as the morphism going between, say, the fundamental representation of SUK and the fundamental FCK over here. How about for SO? Well, in this case, we don't actually have a string which goes directly from SO to SO, but there's kind of an intermediate thing that can exist, which is a SP gauge theory. And it turns out that you can get a supersymmetric boundary condition for an open string going from an SO to an SP. So it's really a composite of composition of two morphisms, if you like, one from SO to SP, and then another one from SP to SO. And then the product of these two is what we would refer to as the link between them. How about for the E6 case? E6, E6, E7, E7, and E8, E8. This is more challenging to study using just a spectrum of open strings, but it can be figured out using what's known as F theory. So this is some strongly coupled version of string theory. And I'm not going to go into too much detail, but the rough idea is that you imagine a collision of two ADE singularities of the same type, and then you can blow up the collision between these, and from that resolution, read off the corresponding degrees of freedom that are kind of trapped in that conformal matter link. That's a very nice story, but I'm probably going to not talk about it too much.
So as you do this blow ups, like what are the constraints on the number of P1s you like? Why should you stop at E8?
Right. So what you do, so in more technical terms, what you do is you write down an elliptically fibered Calabi-Yau threefold, where it has two components with the discriminant locus. And so you specify the Kadai-rotate fiber for each of those components. So this is one component over here, this red one going from upper left to lower right. And then there's another one going from lower left to upper right. So those are two components and they collide against one another. So this is an elliptically fibered Calabi-Yau threefold on a non-compact base. So in the base, you have these two non-compact divisors which are intersecting at a single point. And at that point, the elliptic fiber is becoming very degenerate. So what do? You can't even really define it in some cases. So what do? You perform blowups in the base and you stop precisely when all of the fibers on the resulting components of the discriminant are now in Kadai-rotate form. So that's kind of the clue to stop. And if you try and blow up too much, then what you'll do is you'll actually force it out of that condition, and you'll have a problem even keeping the fibers elsewhere in the proper form. So there's kind of a canonical prescription for taking this singularity and resolving it so that all fibers are of Kadai-rotate form. Does that answer your question?
Does the bundle become unstable in some sense as you go beyond sort of beyond Kadai, or like is there enough stability?
If we blow up even further?
Yeah.
So if you blow up even further, then yeah, there's a sense in which you're going you're violating kind of the Calabi-Yau condition. So so it won't so we wouldn't know how to make sense of it. So
yeah, sure, yeah, thank you.
Okay. So the point though is that for each of these, there's kind of a well-defined answer from at least the F theory background for what this thing actually means. And of course, you could just think about this, as I said, in terms of like world volume degrees of freedom on an M5 ring. But the point is you can go even more microscopically and figure out what's going on in the interior from doing these blowups in the elliptically fibered Calabi-Yau threefold. Okay, so I don't have time to review this in any detail, just to give you the punchline, but you can actually classify all of the elliptically fibered Calabi-Yau threefolds. You can classify all the 60 SCFTs, which can be generated in this way. And kind of the surprise is that it's not a completely wild classification. All of them basically look like generalized quivers. So each one of these circles is one of these gauge groups of A, D, or E type. And then there's links, these conformal matter in between them. And what I'm indicating here by these vertical green lines is that in the interior of this generalized quiver, it's basically a very uniform structure. It always has like a single plateau of the same kind of gauge group. And then over on the left and over on the right, there can be a little bit of decoration of different kinds. And so just by staring at this thing, this generalized quiver, the point is that all of these things always look like a one-dimensional system. So it's natural to ask whether we can pursue that analogy further and actually study what that one-dimensional system might be. Okay, so now I'm going to move on to operators in conformal matter. So I'm going to stop talking about kind of the generalities, and I'm going to start specializing a little bit more to specific kinds of 60 SCFTs. So maybe I should first ask if there's any questions about any of this. Okay, so
So the fact that it's one-dimensional comes from just well, the way the 2,0 theories are constructed. It's like a 5 grains and
well, yes and no. It turns out after the fact that it's always coming from things like M5 brains, but a priori what we're actually doing, so the classification of these things does not proceed by us making that assumption. All we do is we say, let's write down all possible elliptically fibered Calabi-Yau threefolds which have a canonical singularity. So that's a completely different, starting point. But it turns out that indeed, and this was kind of the point of this paper down here, is that we recognized after these earlier classification works had been done, was that indeed most of them can just be thought of as M5 brains probing various kinds of singularities and then deformations of those. But it's not a priori obvious. It's something you kind of rediscover after the fact.
Okay, good.
Great. Any other questions on this part? Okay.
And then you can also have a periodic conditions, right?
Periodic?
I mean, like to make it a loop.
Actually, no, you can't.
Oh no, right. That's if you have a little string theory. Yeah, I think that's.
Yeah, I'll come to an example. Yeah, so if you put a loop in it, you can actually see that there's a kind of winding mode which won't decouple because you have a non-contractible loop in the quiver, and that actually means that you can't reach a SCFT limit. Nevertheless, there's a close cousin of these SCFTs, which is very interesting to study, which are the so-called little string theories, and I will mention those closer to the end. Okay, thanks. Okay, so I mentioned that these CFTs are very hard to study because it's strong coupling and so on. So one of the things that's on the wish list of physicists is to figure out, well, what can we say about the operators? What can we say about this one-dimensional system and operator mixing correlation functions in those operators? This is basically what we do in the context of two-dimensional conformal field theory all the time. You enumerate a set of operators, and you want to know things like the 2-point functions, the 3-point functions, and so on. Can we do the same thing over here in the 60 CFT context? Okay, so to set the stage, let's consider these conformal matter links. What can we say about these links that are here? So in the SUK case, when we're at weak coupling, so not the CFT point, but away from it, we have this hypermultiplet. And in 6 dimensions, one can figure out that in terms of the representation theory of the conformal algebra, that these have so-called scaling dimension 2 under the dilatation operator. Okay. Now, geometrically, we can actually recover this fact as well as what the scaling dimension of the other conformal matter operators is. So using a trick that was actually used in the context of Selberg-Witten theory in this paper a while ago, it was realized in this later paper that I wrote that you could use the Calabi-Yau geometry used to define the conformal matter in the first place. So you take this special limit where the gauge groups are kind of completely shut off and they become so-called flavor symmetries. You can actually use the homogeneity of the Calabi-Yau, the defining hypersurface equation for the Calabi-Yau geometry to read off the corresponding scaling dimension for the operators. So here I'm just exhibiting how it goes for the case of a weakly coupled hypermultiplet. But the point is that this extends rather naturally to all the other conformal matter cases as well, because we know precisely what the analog of this hypersurface singularity is in these more general cases where I talk about G and G. So in this particular case, just from representation theory of the superconformal algebra, one finds the scaling dimension is 2, and therefore the R symmetry representation is 1/2. So it transforms the doublet representation of this SU2. So here R symmetry refers to a symmetry which rotates the supersymmetries of the system. And so everything I'm going to say is supersymmetric, so we should be expecting things to be transforming in some kind of representation of this thing that's also rotating the supercharges. So here it is for the hypermultiplet. And you can do it for all of the other ones as well in the same way. And that was worked out in this paper I wrote a while ago. So you can do it for SU, and here's the different scaling dimensions. And the corresponding spin representation according to SU2. So I'm using physicist notation. So spin half is the fundamental representation. Spin 1 is the one that is a 3-dimensional representation, and so on. You can figure out what the R symmetry is for each of these. Sorry, the R charge is for each of these. Okay, and this has the property of being kind of a composite object, as you'd expect. So for example, for SUK and SUK, it's just spin half. For this SOSO, the one I already mentioned, it looks like a tensor product of two of these, and so it contains this spin 1 or triplet representation. And so what we're basically doing is projecting onto that highest spin representation each time when we talk about the conformal matter. And you can do it for the other ones as well. Here I've actually written down all the curves you get when you do the blow up. So it gets pretty intricate, but you can again see that there's kind of a composite structure emerging. Okay, so this looks like a one-dimensional system. And I just told you that we have these things transforming in specific R-symmetry representations. And we use that to leverage some insight into what's going on in this conformal field theory in the first place. So here's where I'm going to now start talking about the one-dimensional system of interest for my talk today, which is spin chains. But before I do that, maybe I should ask if there's any questions about what I just talked about here, compositeness and scaling dimension of conformal matter. Okay, I don't see anything, so I'll keep going. Spin chains. So there's a particular operator we can form, which is basically just a composition of all the morphisms we have in this quiver. It's really just a product of operators. And so we just go from left to right and we just perform a composition like this. So the point is that each one of these X's, I'll call them, is in a spin R representation of the SU2R symmetry. And if we take the highest weight state in that spin R representation, one can show just based on the general properties of supersymmetry that this thing has is BPS in the sense that BPS here for me just means that its scaling dimension and all its properties are protected against quantum mechanical correction. So in other words, it's a robust thing that we can extract without knowing too much about the microscopic details of the theory. So in the particular case where it's SUK, remember I told you that in this case we had a hypermultiplet and it was spin half. So that's just ups or downs. It's just a product of all ups across. So this is an example of a all spin up composite operator that we can form. This is a BPS operator. It can be studied also using techniques from holography, and we studied it here as well. And then the point is that the scaling dimension of this thing is also controlled by just general properties of representation theory in superconformal algebra. And so we know, first of all, that it's in the bifundamental representation of the leftmost flavor symmetry algebra and the rightmost flavor symmetry algebra. And also, we know its scaling dimension. Since there's n+1 of these links in my counting, it's just n+1 times the scaling dimension of just a single conformal matter link. So this is an operator, and we can actually figure out what its scaling dimension is. So we've now learned something about the kind of microscopic content of this conformal field theory. But what if there aren't all in the highest weight state? So for example, I could still form gauge invariant operators if I take some of these S sub i's and I take them to not be necessarily the highest weight state, but some other state. So I can still form a product of operators like this, and it's still transforming in the bifundamental representation of G left and G right. And what we'd like to know is whether we can say anything about the scaling dimension of these kinds of operators. So this is now looking like a more general kind of spin chain excitation. So one that's not necessarily all ups, but perhaps some number of up states and some number of down configurations. And we'd like to know, what can we say about the scaling dimension of such operators? Knowing this is the analog of saying that I know, say, the L0 eigenvalues in a two-dimensional CFT. So this is something intrinsic to the conformal field theory that we might like to know about. And now supersymmetry doesn't really tell us too much because they're definitely not like holomorphically constructed things, so they can receive quantum corrections. So what I'm going to tell you about is a technique for calculating those quantum corrections using a so-called large R-charge expansion. So it's based on this technique we introduced here, but it's inspired by something that was worked out by Berenstein, Maldacena, and Nastasi quite a while ago, I guess 20 years now. And it's been applied in the physics context in more general settings as proposed by Hellerman, Orlando, and Reffert in this paper here, where again, they started looking at large R-charge expansions. So the general idea is that whenever you have a quantum mechanical state that has a large conserved charge, then you can consider an inverse expansion in that charge as a perturbation series. And that works even if the theory is at strong coupling. So it provides you an alternative way of studying what is going on in that limit. So you're doing perturbation theory, not so much in terms of the parameter of the theory, but rather in terms of the intrinsic charges of the thing itself. Okay, so the idea is this may be a non-BPS operator if we don't take all the S sub i's equal to R, but what if most of them were still S sub I equal to R? Then we would be working in roughly a dilute gas approximation where this thing would be close to BPS, but not exactly BPS. So if you look at the scaling dimensions of the operators, one can argue on general grounds that they will kind of all mix into one another if they had the same R charge. And so you can write down kind of the, once you take the linear combination, which diagonalizes the dilatation operator, you get the leading order contribution, and then a subleading piece, which goes as gamma divided by n squared, and then some further 1 over n to the 4th corrections. So the point is that as the length of the spin chain goes as n, the point is that this can become a very small number, even if gamma is an extremely large number. So that's kind of the trick to getting something out. So even if we don't have a traditional perturbation series, because this coupling here is becoming quite strong, still it's going to be suppressed by 1 over n squared. So we can hope that if n gets big enough, that we can still have this thing be small and subleading. Okay, and this thing turns out to be calculable. So how come it's calculable? So in this large n limit, it turns out that there's also a description in terms of semi-classical gravity on the following space. It's an anti-de Sitter space in 7 dimensions. So in the Euclidean sense, you can think about this as a 7 ball, and then we take the analog continuation to a space-time that has one direction of time. And it's quotiented by an S4 mod gamma G. And this gamma here, this gamma G here, is an ADE subgroup of SU2, which embeds in one of the SU2 factors of SU2 times SU2, sitting as a subgroup inside of SO5. So what's happening is that this quiver can be thought of as literally deconstructing or discretizing a great arc that goes from one side of this S4 over here to the other side. So this left side to this right side. And then each little link here is providing us with where the piece of that quiver sits. So what we're describing just from this qualitative picture in the holographic dual, the gravity dual, is something that involves nearest neighbor hopping of the spin chain impurities. So our down state.
Did you gauge the global symmetry or not?
So in the gravity dual, it's gauged, but it's a 7-dimensional Yang-Mills theory. So so it's filling all of the ADS7, and it sits at the orbifold fixed point of the 4 sphere. So in the gravity dual, it is indeed gauged.
Okay.
Yeah. So the point is, in general, in ADS CFT correspondence, something that is gauged in the gravitational dual becomes a global symmetry in the dual conformal field theory. Does that answer your question?
Yeah, thank you. Thanks.
Okay. So we have this impurity, and it can move around. And just from the structure of that S4 mod gamma, we know it's going to be a local excitation. So it's a leading order. It's just going to be a nearest neighbor hopping effect. Okay, so just on physical grounds, we know that it's going to hop from site to site like this. This is without doing a direct calculation. Now let's do the direct calculation. And as a warm-up exercise, let's do it in the closely related case of a quiver gauge theory in 4 dimensions rather than 6 dimensions. So in this case, you can take this quiver gauge theory, just go down on a 2 torus. So we started in 6 dimensions. Imagine that it was 4 Minkowski 4-dimensional spacetime times a small 2 torus. If we go down, that's what we mean by T2 reduction. We get a 4-dimensional quiver gauge theory, and it has basically the exact same content in terms of gauge groups and matter fields. And in this case, we can just write down a collection of operators. I'll call them O sub j, where I've located one of the x's that is not of highest weight, so the lowest weight state, if it's spin half. And we can just directly try and calculate the 2-point function between 2 such operators. So I give you an OI dagger where I insert it at site. I insert the operator at site, the spin impurity at site I, and then I compare it with what I get at site j. And I calculate a 2-point function like this. So we can read off what it looks like. And you can actually calculate a corresponding mixing matrix. It's called an anomalous dimension matrix. And what we can calculate is actually the precise form of this gamma ij. What does it look like? Here it is. It indeed looks precisely like a hopping term. So we calculate this just using the properties of the supersymmetric gauge theory. And you can actually even read off what the coefficient in front is. Here it is. It depends on some group theory data, such as the dimension of SUK and then 1 over K in our normalization. The point is that this thing is completely well-defined and we can calculate it. So it's indeed just a one-dimensional lattice Laplacian with a particular boundary condition at the left and at the right. So we can, of course, diagonalize this and study the spectrum in this case. So we get the eigenvalues, and indeed, they go like 1 over n squared times a mode number n squared. So provided g squared is, it could be big, but it doesn't have to be that big. It can be quite big, and you could still have a perturbation series available to you. And this is basically the same trick that was used in Berenstein, Maldacena, and Nastase in the context of 4-dimensional n equals 4 super Yang-Mills theory, so a theory that had 16 rather than 8 supercharges. But the same trick works in this context as well, that so the point is that even if the gauge coupling is getting really, really big, you have a 1 over n suppression because the length of the spin chain is so big. And this allows you to access regimes that would otherwise be inaccessible because you can increase the value of this gauge coupling to very large values. So it's a different kind of a perturbation series, not so much in G, but rather in 1 over n, or more precisely, G over n. So this is the hopping. And we've actually now calculated what that Hamiltonian is. What is it? It's just the Heisenberg spin chain. So the standard XXX spin chain. And the point is that here we've actually observed directly, just by direct computation, that this thing is integrable. And we can actually calculate the 1 over n squared spectrum at low impurity numbers. At higher impurity numbers, one can worry that the approximation here is going to break down because there will be different kinds of quantum mechanical corrections, which would not necessarily be captured by the spin chain. But at low impurity number, everything is fine, and it's indeed an emergent integrable system coming out for this 4D quiver gauge theory. Let me also comment, I forgot to put in some citations here. Other folks have, of course, considered related 4D n equals 2 systems and integrability in that setting. But as far as we were aware, we did not see anybody talking about this particular kind of quiver gauge theory and this particular class of operators. For some reason, people have been considering different kinds of n equals 2 gauge theories that were trying to mimic more the n equals 4 case. This is really more purely treated in terms of n equals 2 by itself. Okay, so perhaps from your perspective, this is a bit.
What about the work by Rastelli, Gade?
Rastelli and Pomoni, right? So what they did is they took a different kind of limit. So they actually considered the case where you don't have very many quiver nodes. But what they did is in 4 dimensions, you have adjoint valued scalars. And so what they did is they took this scalar, let's call it, I don't know, Z, and you take trace of Z to the J, and you take J to be very, very big. That's very much like what BMN did. And that's the integrable system that they looked at in detail. So they took Z to the J, and then they imagined sticking in various kinds of impurities in that system.
So there was another a series of papers by Rastelli, Gade, maybe Pomoni was there too, but I think they had some negative result in the sense that integrability was broke down.
You have at 2-loop order, yeah. But again, I think it was in a different sector of operators. It wasn't in this operator sector.
Okay.
So I don't know what happens here. I mean, this one I actually suspect works better than the one that they considered, because there's a sense in which this thing here is really inherited from the like an orbifold projection of the n equals 4 super Yang-Mills theory case. So so that's something that Bizard and Roybon looked at shortly after Bizard's stuff on n equals 4 super Yang-Mills. The point is that they looked at, so Bizard and Roybon did look at something very close to this, and they indeed observed like integrability was going to persist, I think, to fairly high order in perturbation theory, but I don't remember exactly. So indeed, the Rastelli-Pomoni thing was basically negative, but this is a different kind of sector. And the first point is just that at 1-loop order, which is the work at the level I'm working at here, it's just a true statement that it is an integrable spin chain, because this is it. Now, what you could worry about is at like next to leading order, you'll have to worry about next to leading order interactions. And then of course you could worry, well, does it remain integrable? This I have nothing to say about, but I think it's in better shape, or it's potentially a more promising sector than the Rastelli, Pomoni, and and Rastelli-Gatti operators.
I see. Yeah, thank you.
Okay, but yeah, so as far as we've actually tested it though, yeah, we're still at just one loop order, but I think on general grounds, it's going to work better because of this relation to the Beiser-Roybon story. Okay, so beta ansatz for this. Again, this is a pretty classic result. We're talking about beta ansatz for an integrable spin chain with open boundary conditions. Here I've just written down what it is. And from this, the point is that there's an energy that you can read off in terms of the so-called rapidities. Here they are. This PJ is just the spin wave momentum as we go along. And the point is that the scaling dimensions of our 60 CFT are just encoded in the energies of that one-dimensional spin chain. So these are known. All of this is known on the right-hand side in principle. I mean, of course, you still have the task of solving this equation, but at a practical level, or sorry, at a conceptual level, this kind of solves the problem. Extracting actual numbers is of course more challenging, especially at higher impurity. But the point is that this is in principle, this is in principle the solution. Okay, now the thing I talked about mainly was in the case of the A-type quiver gauge theory. Now remember I mentioned, here, let me go back. I mentioned that we had these other conformal matter sectors with different R symmetry representations. Based on everything I've said, it's very natural to expect, especially in the context of the holographic dual, where there doesn't seem to be too much distinction between SU and SO and so on, in terms of how the excitations are moving around. We expect there to also be an infinite number of conserved charges in an integrable system for these other cases as well. And so what are we doing? We're talking about a spin chain that has a particular spin excitation, no longer spin half, but instead spin 1, or 3 halves, or 2 or 3, depending on whether it's SO, E67, or E8. And we can again ask, okay, what is the spin chain Hamiltonian in this case? And what is the corresponding solution to the beta ansatz? Now, in this context, this is one of the triumphs of kind of the beta ansatz. You can determine the actual Hamiltonian directly from the assumption of integrability. Moreover, we can just read off what the scaling dimensions are. So here's what it is, just as a review. So this is me just plugging in for the different values of the R charge. So, doing this as a direct calculation for these cases, we don't know how to do. And the reason is because this conformal matter is strongly coupled, even in 4 dimensions. So we don't know how to do this directly, but because of integrability, so we jump ahead and assume it's integrable. We know this one is integrable from a direct calculation. And once we assume that, we can actually start reading off all the other ones. So this is telling us about also, if we reverse the order of logic, about how the composite operators are interacting with one another in this more complicated case of conformal matter. Okay, and here again is the beta ansatz. So the only modification is that S is changing. Before it was 1/2 for a spin half representation, and now it's different. But that's about it. That's the only change in going from A-type to the other more general conformal matter cases. Okay, so this is all in the context of 4 dimensions. How about 6 dimensions? So as I was mentioning, 6 dimensions is intrinsically more difficult precisely because we don't have a gauge coupling to speak about, or do we? So in 4 dimensions, we can talk about a marginal coupling, a dimensionless parameter, and we can take it to be small if we want, and then we can extrapolate up to big values. In 6 dimensions, the gauge coupling turns out to not even be a dimensionless quantity. It turns out to be dimensionful. It's set by the vacuum expectation value of a real scalar, it's so-called tensor multiplet scalar. But we have a hint for what to do from the kind of ADS7 times S4 mod gamma holographic dual. That thing, as I mentioned, is deconstructing the great arc that goes between the 2 fixed points on the sphere. And so there's a sense in which the holographic dual actually provides a canonical regulator in the gauge theory system. So even though the gauge coupling is getting big, there is a sense in which it's actually regulated and fixed to a particular size. So the gauge coupling, one can work out just from the scaling relations for BPS strings from coming from like M2 branes wrapped stretched between these 2 nodes, for example. This goes as n to the 2/3, where n is again like roughly the length of the quiver, the number of nodes in the quiver. And then we have the 11-dimensional Planck length over here. There's a corresponding effective gauge coupling, which is indeed extremely large, going as n to the 2/3. But this is actually enough for us to extract a corresponding gauge theory analysis in terms of this very large gauge coupling. So you'll notice that this is an extremely large number. So it, as n goes to infinity. But the point is that we can still use it to kind of start analyzing things in a 1/n² expansion. So you can do exactly the same calculation that we did in 4 dimensions. And again, you discover that there's a kind of nearest neighbor interaction term like this for the 2-point functions. And so you get this kind of expansion. So here the anomalous dimension matrix is going like this n to the 2/3. That's our gauge, effective gauge coupling. And then we have a 1/length squared. So the point is that even though n to the 2/3 is extremely large, it's dominated by this 1/n² piece. The final caveat is that compared with 6 dimensions versus 4 dimensions, there's an additional condition because we can't allow momentum to kind of leak from left to right. And this just means that in terms of the spin wave excitations, we actually demand that they always sum on net to 0. So it's just a technical condition on what kind of operators we're allowed to entertain. But the point is that we still have a perturbation series expansion in 1/n, or more precisely, n to some fractional power, but it's getting killed off as n goes to very large numbers. So it's a small correction to the kind of supersymmetric protected quantity. So again, the beta ansatz is in play, and there's almost no material difference from what we did in the 4-dimensional case. That's the key point. The 4-dimensional calculation, modulo a few subtleties involving, say, the momentum conservation, and the fact that the gauge coupling is now fixed as a particular power of n, it's all pinned down. And this lambda g here is, again, something that we read as being order n to the 2/3 divided by n². Okay, so in other words, we can read off, again, the 6-dimensional case both for that and the conformal matter situation as well. Any questions about that? So now I've told you that the spin chain that we just talked about lifts directly into the 6-dimensional setting. So now we have kind of a microscopic enumeration of what is going on in terms of these operators here. And we see an integrable spin chain for the A, D, and E series of these conformal matter quiver gauge theories. Okay, maybe I'll move on to generalizations. I guess I'm almost out of time, so maybe I'll be fast about this. So Peter was already asking about what if you change the boundary conditions. So if you have a 6D CFT like this, you can consider gauging the flavor symmetry here and here, and you'll wind up with a circular loop. And this is giving us a little string theory. From our perspective, this does almost nothing. It just changes the boundary conditions on the beta ansatz in the spin chain. That's it. What else can you do? Well, here I focus primarily on the case of SU2R symmetry, but in this work that's going to appear hopefully soon, we considered, what if we extend this now to representation theory, not just of the SU2R symmetry, that's just associated with this /1 piece over here, but the full superconformal algebra, like this. So SU2 is one of the subalgebras. SO6, 2 is the conformal algebra. So SO6, 2 times SU2 is just the bosonic part of that super Lie algebra. And you can consider more general spin chain excitation. So now they're not just controlled by highest weight states of SU2R, but rather highest weight states of the entire superconformal algebra. Okay, so we take composite operator like this. And you can write down the corresponding beta ansatz for this case as well. So here we have a highest weight vector over here on the left-hand side. I guess I've switched my notation slightly, but on the right-hand side, we have the, I'll refer to it as the Cartan for the super-Dynkin diagram. Now, an important subtlety relative to the case of where this is a Lie algebra is that when it's a super Lie algebra, there's not necessarily a unique choice for the MIJ. It depends on what you want to analyze. So things that associated with small excitations of the ground state in one presentation of MIJ can, by super Weil reflections, be related to something that looks quite complicated in another presentation of the super Dynkin diagram. So to illustrate that, we can consider different kinds of excitations. So the ones I focused on primarily were these so-called Y daggers. Here's a hypermultiplet, and I'm decomposing it into different kinds of states you can generate, treating this as a primary operator and then descendants in the superconformal algebra. Y dagger, the presentation of the super Dynkin diagram that's most convenient there is this one here. Here you can clearly see an SO6, and here you can clearly, an SU4, which is accidental to an SO6. And then you have the SU2R symmetry. That's the one we focused on primarily, these Y dagger insertions. And if you pick other kinds of impurities that you're interested in, in terms of making them close to the excitation associated with X, you can pick other choices for this super-Dickin diagram. And we enumerate all the different choices you can get by super Wow reflections and what the corresponding kind of minimal fluctuation in terms of impurity is associated with it. So here's one sector, I'll call it SU1/1, associated to fermionic excitations. And dx corresponds to a particular derivative in a light cone direction for X. These things were all studied in some form in the context of n=4 super Yang-Mills, or the analog of that was studying the n=4 super Yang-Mills sector, where it was again kind of extrapolated from certain subsectors, how it would kind of extend via integrability to the entire superconformal algebra. We're playing exactly the same game, except now the superconformal algebra is OSP 6,2/1 instead of a different. Okay, can you go beyond the XXX spin chain? Indeed, you can. So in this paper on kind of what's called like the cubic construction associated with this, one can break the SU2R symmetry. This is a Higgs branch flow, and you can start generating things that don't necessarily respect the SU2R symmetry rotation. So A here is an index labeling that SU2 representation. The technical point, which we don't know how to get beyond at this point, is that when you also do this Higgs branch flow, you typically also trigger external magnetic fields to be switched on the spins. So I'm not sure exactly what we get. It may be a bit more complicated than just something like an XXZ spin chain because of these background magnetic fields. And I'm not sure I even know how to solve it, but that's, it seems to be, if we could solve it, we would have actually access to what's going on in an entire renormalization group flow for the 6D CFT. Okay, and more general operators you consider in the holographic dual, you can consider closed loops, other kinds of gauge invariant operators. All of these things are things that have not really been studied in any great detail and provide us with another way to kind of access the system. Okay, so I'm basically done. Let me just summarize and tell you about some future things that might be interesting to look at. So what did I tell you about? I told you about how to use basically the geometry of branes and also the extra dimensions and strings to construct 6D CFTs and 4D CFTs. And they basically look like 1D systems. And this one-dimensional structure we interpreted in terms of a spin chain. And we actually, by performing direct calculations, saw hints of integrability in these sectors. So for the future, this was already mentioned, one natural question is, does this integrable structure persist at higher order in perturbation theory? All I did here was kind of the leading order calculation. What happens if we include next to leading interactions? Does it continue or does it break down as happened in other subsectors of n=2 theories? And related to my last comment about generalizations and other operators, another natural question is whether there's other kind of protected subsectors that we can also analyze using similar spin chain technology. So I'll stop there, and thanks for staying awake or whatever.
Right, thank you very much, Jonathan. And so please questions. Yeah, I guess fellows are getting tired a bit, yeah. Okay, so let me ask maybe a quick one. So the you know, in n=4 integrability, they talk about what is it, like the full solution using TBA and this Y system kind of thing, right? Something pretty much every question they ask, we can ask here, right? So like
Correct.
They expect to get some. I mean, do you think one can construct something like this here? So some, you know, sigma, like the torus sigma model. What?
Yeah. So in fact, one thing that we have a kind of that we would like to do in the future is there's another thing which you often have, which is like this, the emergent geometry coming out from Y system, study of Y system. It's natural to suspect that because we have a direct like geometric realization of these systems, that quantum curve which is emerging has something to do with the actual F theory geometry. Now, what the
like you mean like this spectral, like quantum spectral curve?
Yeah, exactly. That quantum spectral curve.
Quantum spectral curve will be somehow directly obtained from F theory, right? So
that's right. So it's a natural expectation that something like that should happen. I don't know how it would work or whether it really does work. I mean, I've tried for a while and nothing kind of like jumped out. But in that sense, I'm actually optimistic or hopeful that there might be some way to actually make a more direct contact with geometry. So in the context of n=4 Yang-Mills, right, it's just like some remarkable fact that you observe. like where it came from.
Yeah, and their construction of a quantum spectral curve is highly non-trivial, right? So it's
yes.
Yeah.
Yeah. So what I would hope for is that somehow the F-theory geometry would know more directly about this, but I don't know how to see it right now. But yeah, so all the questions that you ask in the n=4 context, they all have avatars in this setting. I will say that there's actually something you can do in this context that you cannot do in n=4 Yang-Mills, which is, and it's something that we're looking into now, is, so if you go back to, so in 4 dimensions, just go to 4-dimensional case. Well, I don't know, where did I put it? Any one of these quibbles. So we had like SUK gauge theory here. So the way that you make the holographic dual in the 6-dimensional context is by taking a large number of quiver nodes, by making that very large. Now, that's not what you do to make a holographic dual in 4 dimensions. In 4 dimensions, the way you would make a holographic dual is by increasing the rank of the gauge group on each one of the nodes. And so you could get a holographic dual even if the length of the quiver is very small. So now you can play a game where you vary the length of the quiver, making it either big or small, but you always take the large rank limit for the gauge group. So this is an extra knob or degree of freedom you have relative to n=4 Yang-Mills.
Yeah, because there the holographic dual is fixed. There's just only one.
Yes, exactly. So here we have another kind of discrete parameter. And the very natural question is, what is the phase structure of this system as we change the ratio between the rank here and the length of the quiver? So there's a whole phase diagram here that we should be able to access just from this general point of view. So the case we have
what happens with those, say you have E6 or 8, like as you ask, I guess what happens as you go down to 4 dimensions from, like, as you compactify it, or like, so since there's no analogs of these guys in n=4 integrability, right? What happens when you try to compactify it towards this? Okay, I guess.
Yeah. So here I tried to mention that briefly. So the point is that you can still talk about those guys. Those guys don't have like a 4D holographic dual because because E6 has fixed rank. You're never going to make it.
And they do not describe any dilatation operator in n=4 Yang-Mills, right? It's just thing in itself, in a sense, right?
Yeah, as far as I know, it's just a thing by itself. But the point is that we kind of know from beta ansatz what we should expect, because we know the spin of the excitation.
Okay,
So we know from integrability and the spin of this thing what the excitation spectrum is, and we can read off again the scaling dimensions. But there's no direct holographic dual in 4 dimensions. In 6 dimensions, there's still a holographic dual.
Sure. Yeah.
That's controlled by the length of the spin chain.
Excellent. Yes, that sounds really exciting. Yeah. Other questions? Great. So thanks, Jonathan, again. Yeah. So that's it for tonight or this morning, whatever time it is. And yeah, so we'll have another 3 more talks tomorrow. Yeah. So see you guys then. Bye. Thank you very much. Oh, yeah, and then please email me your slides, all the speakers. I'll put them on the website. Yeah. Thanks. Bye.
Bye.